Good evening, and welcome to the Late Lab. I'm very glad you've joined me. Before we settle into tonight's subject, let me know where you're listening from. Perhaps you're tucked beneath the covers, resting on a quiet sofa, travelling home beneath the evening lights, or simply taking a little time away from the noise of the day. Wherever you happen to be, I hope you feel comfortable, unhurried, and ready to let your thoughts wander somewhere strange. If these calm journeys through science help you relax, leaving a like and subscribing is a simple way to support the channel and help more curious night owls find their way here. And if you have already subscribed, thank you. It genuinely means a great deal to me, and I'm very grateful that you continue to spend your evenings here. Tonight, we are stepping into one of quantum physics' most famous and easily misunderstood ideas, superposition. It is the peculiar possibility that a single quantum system can contain two different alternatives at the same time, right up until an interaction forces one clear result to appear. I'll do my best to explain it without placing your own bedtime into a superposition of asleep and completely fascinated. Although considering the subject, no outcome can be guaranteed. So make yourself comfortable, allow the day to grow a little quieter, and let us begin. How can one thing be two things at once? And why does the ordinary world never seem to behave that way? The ordinary world seems to have very firm opinions about what an object is allowed to be. A chair is either beside the table or across the room. A lamp is switched on or switched off. A coin resting beneath a hand is either showing heads or showing tails, even if nobody has looked yet. The details may be unknown, but we assume the object itself has already settled the matter. Quantum mechanics describes something much less familiar. A quantum system can exist in a superposition, meaning that its state may contain several distinct possibilities at the same time. Yet whenever that system is directly measured, the result is not a blurry mixture of outcomes. The detector records one definite event. An electron appears at one point. A photon is found with one measured polarization. An atom is detected in one energy state. The strange part lies in the relationship between the range of possibilities present before the measurement and the single outcome that appears when the measurement is made. This is the central puzzle of quantum superposition. How can one physical system contain several possibilities while every observation produces only one answer? It is tempting to imagine a particle quietly making copies of itself. Perhaps one electron slips down one path, while an identical second electron takes another. But that picture is usually misleading. Superposition does not mean that a single particle is divided into a collection of ordinary miniature objects, each living a separate classical life. Instead, the quantum state contains measurable probability amplitudes associated with different possible outcomes. These amplitudes describe how the possibilities combine, evolve, and interfere. They are not merely percentages written beside a list of options. Probability amplitudes can reinforce or cancel one another, producing effects that ordinary uncertainty cannot explain. Consider an electron moving toward an apparatus with two available routes. Classical intuition suggests that it must follow the first route or the second, whether or not anyone knows which one. Quantum mechanics can instead describe the electron with one state containing an amplitude for the first path and another amplitude for the second. The two contributions remain parts of a single quantum state. If the apparatus preserves their coherence, they can later interfere. A photon provides another example. Light can be polarized in different directions. A photon prepared in a diagonal polarization may be represented as a superposition of horizontal and vertical polarization relative to a particular measuring device. When measured in that arrangement, the photon is recorded as either horizontal or vertical. It is never registered as half of each. Nevertheless, the state before measurement cannot always be understood as a photon secretly carrying one of those two answers. An atom can also occupy a superposition of energy states. Carefully applied electromagnetic radiation can prepare it in a coherent combination of two allowed energy levels. The atom state then evolves as the relative phase between those components changes. Later measurements reveal definite outcomes. but the behavior observed across many repetitions depends on the superposition that existed beforehand. These examples involve different properties, yet the same principle runs through all of them. Position, path, polarization, energy, and spin can each form the basis of a quantum superposition. The exact meaning depends on which physical property is being discussed and how it will be measured. This is why the phrase "one thing can be two things" is both useful and slightly dangerous. It captures the surprise but not the full precision. A quantum system is not ordinarily observed displaying two contradictory classical outcomes at once. The detector does not show an electron arriving in two places during one measurement. It records one localized event. The superposition belongs to the quantum state and to the pattern of possible results, not to a final record containing mutually exclusive answers side by side. Superposition is also different from simple ignorance. Imagine a coin hidden inside a box. It may be heads or tails, and you may have no idea which. That uncertainty does not normally create interference between heads and tails. The coin already has one orientation, while your knowledge remains incomplete. A coherent quantum superposition behaves differently. Its components possess a definite phase relationship, allowing their amplitudes to combine. That relationship can change the probabilities of later measurements. Constructive interference can make some results more likely. Destructive interference can make others less likely, or even reduce their probability to zero. A classical list of unknown alternatives cannot generally reproduce this behavior, nor is superposition simply another word for randomness. Randomness concerns which result appears when a measurement is made. Superposition describes the structure of the state before that result is recorded. The two ideas are related, but they are not interchangeable. It is also not a literal physical splitting into smaller portions. An electron arriving at a detector delivers its full electric charge. A photon transfers a complete quantum of energy associated with its frequency. The outcomes are localized and whole, even when the state that led to them included several coherent alternatives. These distinctions matter because superposition is not an optional philosophical story placed on top of quantum mechanics. It is built into the mathematics and tested through experiments. Interference patterns produced by photons, electrons, atoms, and molecules depend on it. Atomic structure cannot be described correctly without quantum states. Modern spectroscopy, atomic clocks, quantum sensors, and quantum computers all rely on the controlled preparation and manipulation of superpositions. The equations work with extraordinary accuracy, even when the underlying picture feels almost impossible to visualize. That difficulty may reveal more about human intuition than about nature. Our instincts developed among warm, crowded, strongly interacting objects. A football does not remain delicately associated with two visible trajectories because air molecules, light, thermal motion, and countless other interactions rapidly destroy the coherence between alternatives. Large objects constantly exchange information with their surroundings. Their quantum possibilities become entangled with the environment so quickly that only stable, effectively classical outcomes remain apparent. Microscopic systems can be isolated far more successfully. Under carefully controlled conditions, their alternatives remain coherent long enough to interfere and reveal the structure of the quantum state. So the apparent absurdity of superposition does not arise because quantum mechanics is careless about reality. It arises because reality at very small scales follows rules that ordinary experience rarely allows us to see. The universe is not necessarily making things up as it goes. It is simply using a language of possibilities that our everyday senses were never designed to read. Before quantum mechanics, physics treated possibilities as reflections of incomplete knowledge rather than features of nature itself. An object was assumed to possess definite properties at every moment, whether anyone had measured them or not. A planet had a particular position. A stone had a particular speed. A coin hidden beneath a hand was already showing heads or tails. The observer might not know the answer, but the answer was presumed to exist. Imagine placing a coin on a table and covering it before anyone sees how it landed. From your point of view, there are two possibilities. It could be heads, or it could be tails. Yet classical reasoning says the coin is not genuinely in both conditions. It has already settled into one definite orientation. The uncertainty belongs to you, not to the coin. This distinction seems obvious because it matches almost everything encountered in ordinary life. A closed cupboard does not place a cup in every possible location on every shelf. A parked car does not become a mixture of facing north and facing south simply because nobody has checked. Hidden facts remain facts. Classical physics was built upon this assumption of definiteness. In the mechanics developed by Isaac Newton during the 17th century, particles were represented as objects occupying particular positions and moving with particular velocities. Forces altered their motion according to mathematical laws. Given the starting position, speed, direction, and forces acting upon an object, its later trajectory could be calculated. A thrown stone followed one continuous path through the air. A planet travelled around the sun along a predictable orbit. The moon did not test several routes before selecting one. It moved through a definite sequence of locations moment by moment. Newtonian mechanics was astonishingly successful. It described falling bodies, tides, projectiles, machines, and the motion of the planets with a precision that transformed science. It suggested that beneath the apparent complexity of the world lay a stable and orderly system of causes and effects. The French mathematician Pierre-Simon Laplace later expressed the most ambitious version of this classical ideal. He imagined a hypothetical intelligence that knew the exact positions and motions of every particle in the universe, together with all the forces acting between them. With unlimited calculating power, such an intelligence could determine both the future and the past from a single moment. This idea became known as Laplace's demon, although the imagined intelligence was not intended as a supernatural creature. It represented complete knowledge of a perfectly deterministic universe. In this picture, probability did not arise because nature itself contained several unresolved outcomes. Probability appeared because human beings lacked enough information. The toss of a coin seemed random only because nobody knew every detail of its initial motion, the force of the throw, the surrounding air, the rotation of the coin, and the surface on which it would land. If all those details were known with perfect precision, classical mechanics suggested that the outcome could be predicted. Chance was simply ignorance wearing a slightly dramatic coat. Yet classical physics did not describe everything as a particle. Waves behave differently. A particle could be pictured as a localized object following a path, while a wave spread across a region. Waves could overlap, pass through one another, and produce interference. Drop two pebbles into calm water, and each creates expanding ripples. When the ripples meet, their heights combine. Where two crests arrive together, the water rises higher. Where a crest meets a trough, the disturbances partially cancel. Afterward, the waves continue travelling. They have overlapped without permanently destroying one another. This is an example of the classical superposition principle. When a system behaves linearly, the combined disturbance is found by adding the individual disturbances. Sound waves behave in the same general way. Two musical notes can travel through the same room at once. The air pressure variations produced by each sound overlap. At some locations and times they reinforce one another. At others, they weaken one another. Electromagnetic waves also superpose. Radio waves, visible light, microwaves, and other forms of electromagnetic radiation can cross the same region of space. Their electric and magnetic fields combine according to the equations developed by James Clerk Maxwell. Constructive interference occurs when waves align so that their disturbances reinforce. Destructive interference occurs when they oppose one another, reducing the total disturbance or, under ideal conditions, cancelling it almost completely. There was nothing especially mysterious about classical wave superposition. The waves were real, measurable disturbances of water, air, or electromagnetic fields. Their amplitudes represented physical quantities such as displacement, pressure, or field strength. When two waves overlapped, those physical quantities simply added together. Classical particles and classical waves therefore occupied two clearly separated categories. Particles were localized. They moved along definite paths and arrived at definite places. Waves were extended. They spread through space, overlapped, and interfered. For a long time, that division seemed perfectly sensible. The difficulty began when experiments showed that microscopic entities refused to remain politely inside either category. Electrons could be detected as localized impacts, as though they were particles. Each electron arrived at a particular place on a screen and transferred a definite amount of charge. Yet collections of electrons could also produce interference patterns, the characteristic signature of waves. Light created the same problem from the opposite direction. It travelled and interfered like an electromagnetic wave, yet it exchanged energy in localized packets called photons. The old categories began to blur. A classical particle could not travel through two routes and interfere with itself. A classical wave could spread through both routes, but it was not expected to arrive as a single localized event. Microscopic systems seemed to display features of both, while fitting completely into neither description. Quantum mechanics eventually replaced the old picture with something more abstract. Instead of assigning every system a definite collection of classical properties, it described the system with a quantum state. That state could contain probability amplitudes associated with several possible outcomes. These amplitudes could combine and interfere like waves, but they did not represent ordinary material spread through space in the classical sense. When a measurement occurred, the result appeared as a definite event, often resembling the behaviour of a particle. This was a profound change. In classical physics, possibilities were merely things that might be true because the observer did not yet know the facts. In quantum mechanics, multiple possibilities could become components of the physical description itself. The hidden coin remained either heads or tails. The unmeasured electron was something more difficult to express. Its possible paths could remain coherent, influence one another, and produce consequences that no ordinary collection of unknown classical trajectories could explain. The world had not stopped obeying rules, but the rules no longer insisted that every microscopic object must always carry a complete set of familiar, predetermined answers. Particles and waves had once seemed like separate ingredients of nature. Quantum theory revealed that both were incomplete glimpses of a deeper structure, one in which definite events emerge from states built from possibilities. For much of history, light seemed to offer two competing stories about what it was. In one story, light behaved like a stream of tiny particles travelling in straight lines. This picture appeared to explain sharp shadows, reflection, and the way beams moved from one place to another. In the other story, light behaved like a wave, spreading through space, bending around obstacles, and combining with itself. At first, both descriptions had strengths. The difficulty was deciding which one nature had actually chosen. A decisive clue arrived in 1801, when the English scientist Thomas Young performed an experiment that became one of the most important demonstrations in physics. Young allowed light to pass through two narrow openings placed close together. Beyond them, he observed the light on a screen. If light consisted only of ordinary classical particles, the natural expectation was simple. Particles passing through the first opening would create one bright region. Particles passing through the second would create another. The screen should display two overlapping patches of illumination. That was not what appeared. Instead, Young observed a sequence of alternating bright and dark bands. The light did not merely gather behind the two openings, it formed an interference pattern. The reason becomes clearer by imagining the light as a wave. Each narrow opening acts as a new source from which the wave spreads. The two spreading contributions overlap as they travel toward the screen. At some points, the crests of the two waves arrive together. Their effects reinforce one another, producing constructive interference and creating a bright band. At other points, the crest of one wave arrives with the trough of the other. Their effects oppose one another, producing destructive interference and creating a dark band. The precise spacing of these bands depends on the wavelength of the light, the distance between the openings, and the distance to the screen. Different colours produce slightly different patterns because different colours correspond to different wavelengths. Young's experiment gave powerful support to the wave description of light. The alternating bands were not an accidental blur or an imperfection in the equipment. They were an orderly pattern produced by the addition and cancellation of waves travelling along two routes. The wave picture became even stronger during the 19th century through the work of James Clerk Maxwell. Maxwell united electricity and magnetism within a single mathematical theory. His equations showed that changing electric fields could produce magnetic fields, and changing magnetic fields could produce electric fields. Together, these disturbances could travel through space as electromagnetic waves. When Maxwell calculated their speed, he found that it matched the measured speed of light, roughly 300,000 kilometers per second in a vacuum. The implication was remarkable. Visible light was an electromagnetic wave. This theory placed light within a much larger family. Radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and gamma rays are all forms of electromagnetic radiation. They differ mainly in wavelength, frequency, and energy. By the end of the 19th century, the wave description appeared deeply secure. Light travelled as oscillating electric and magnetic fields. It could reflect, refract, diffract, and interfere. The case seemed almost closed. Physics has a habit of becoming most troublesome just as everyone begins packing away the equipment. A new problem emerged from the study of thermal radiation. Heated objects emit electromagnetic radiation, and classical theories fail to describe the observed distribution of energy across different frequencies. In 1900, Max Planck found a mathematical solution. He proposed that matter could emit or absorb energy only in discrete amounts. These packets were later called quanta. Planck's relation can be expressed in words as the energy of a quantum equals Planck's constant multiplied by the frequency. This proposal was initially a way of reproducing the measured spectrum of heated objects, yet it introduced a deeply unfamiliar idea. Energy exchange might not occur in an infinitely smooth flow. It might happen in indivisible steps. Albert Einstein pushed the idea further in 1905 while analysing the photoelectric effect. In the photoelectric effect, light striking certain metal surfaces can eject electrons. Classical wave theory suggested that increasing the intensity of the light should eventually provide enough energy to release electrons, regardless of the light's frequency. Experiments showed otherwise. Below a particular threshold frequency, no electrons were released, even when the light was made more intense. Above that threshold, electrons appeared without a noticeable delay. Increasing the frequency increased the energy of the emitted electrons, while increasing the intensity mainly increased how many electrons were released. Einstein explained these observations by proposing that light transfers energy in localized packets. Each packet carried energy determined by the frequency of the light. These packets later became known as photons. A single electron could absorb energy from a single photon. If the photon carried enough energy to overcome the binding of the electron within the material, the electron could escape. If the frequency was too low, increasing the number of insufficiently energetic photons did not solve the problem in the simple classical way. The explanation was successful, but it reopened the question of what light actually was. Young's experiment showed that light interfered like a wave. Maxwell's theory described it as an electromagnetic wave travelling through space. Yet the photoelectric effect showed light exchanging energy through localized discrete events. A wave appeared to spread across space. A photon appeared to arrive as one indivisible packet. The old choice between wave and particle was no longer adequate. Quantum theory did not resolve the problem by saying that light secretly changes costumes. A photon is not simply an ordinary classical particle during detection and an ordinary classical wave during travel. Both classical pictures are incomplete. A photon is represented by a quantum state. That state can contain probability amplitudes associated with different possible paths, polarizations, energies, or other measurable properties. In a double-slit experiment, the photon state may contain an amplitude connected with the first opening and another connected with the second. As long as the two paths remain indistinguishable and coherent, those amplitudes combine. Where they reinforce one another, detection becomes more likely. Where they cancel, detection becomes less likely. Across many repeated trials, individual localized detections gradually form the interference pattern. Each photon is detected at one place. The pattern, however, depends on contributions associated with both possible routes. This is where quantum superposition becomes essential. The photon state is not merely an unknown classical path waiting to be discovered. If it were simply taking one definite route while observers remained ignorant, the characteristic interference between the alternatives would not arise in the same way. The superposition has measurable consequences. The history of light therefore reveals why quantum theory became necessary. Superposition was not invented because physicists wanted reality to sound mysterious. It emerged because repeated experiments demanded a framework in which wave-like interference and particle-like detection could belong to the same physical system. Light did not fit cleanly into either classical category. It travelled through experiments according to amplitudes that could spread and interfere, yet it produced definite, localized events when energy was exchanged. Nature had not chosen between wave and particle. It had revealed that both ideas were shadows of something deeper, and that possibility itself could become part of the physical description. Once light had begun behaving like both a wave and a particle, an unsettling possibility appeared. Perhaps the confusion did not belong to light alone. Perhaps matter itself, the solid substance of atoms, electrons, stones, and people, also possessed a hidden wave-like character. In 1924, the French physicist Louis de Broglie proposed exactly that. Albert Einstein had shown that light, long understood as a wave, could exchange energy in discrete packets called photons. Louis de Broglie wondered whether nature might possess a deeper symmetry. If something traditionally described as a wave could behave like a particle, perhaps something traditionally described as a particle could also behave like a wave. He suggested that every material particle possesses an associated wavelength determined by its momentum. The relationship can be stated as the wavelength equals Planck's constant divided by the momentum. Planck's constant is the fundamental quantity introduced by Max Planck at the birth of quantum theory. It sets the scale at which quantum effects become important. Momentum describes the quantity of motion carried by an object and depends on both its mass and its velocity. The relation means that a particle with greater momentum has a shorter wavelength. A slowly moving electron may possess a relatively long matter wavelength, while a fast electron has a shorter one. For ordinary objects such as a book or a bicycle, the momentum is so large compared with Planck's constant that the associated wavelength becomes unimaginably tiny. This helps explain why tables do not appear to diffract around doorways, which is probably convenient for everyone involved. For electrons, atoms, and other microscopic systems, however, the wavelength can be large enough to produce measurable effects. Louis de Broglie's proposal was striking because there was initially no direct experimental evidence that particles of matter behaved as waves. An electron had charge and mass. It could be accelerated through electric fields and detected as a localized object. giving it a wavelength seemed like a bold extension of an already strange theory. Yet the idea soon received powerful experimental support. In 1927, the American physicists Clinton Davison and Lester Germer directed a beam of electrons toward the surface of a nickel crystal. A crystal contains atoms arranged in a regular repeating structure. The spacing between layers of atoms can act somewhat like the lines of a diffraction grating. When ordinary waves encounter regularly spaced structures, their scattered contributions can reinforce in some directions and cancel in others. The resulting pattern depends on the wavelength of the incoming wave and the spacing within the material. Davison and Germer measured how many electrons were scattered in different directions from the nickel crystal. They found distinct peaks in the detected intensity. The electrons were not simply bouncing away in a smooth, featureless distribution. They were producing a diffraction pattern. The pattern matched the wavelength predicted by the relation proposed by Louis de Broglie. Electrons had behaved as waves. Around the same period, the British physicist George Paget Thomson carried out related experiments by passing electrons through thin metal foils. The electrons produced rings characteristic of diffraction, once again demonstrating wave-like behaviour. There was a pleasing historical irony in this result. George Paget Thomson was the son of Joseph John Thomson, who had received recognition for identifying the electron as a particle. The father helped establish the electron's particle character, while the son helped demonstrate its wave character. Physics occasionally arranges its family stories with suspicious neatness. These experiments did not show that electrons were ordinary waves of material spread continuously through space. When an electron reached a detector, it still produced a localized event. An electron could strike a photographic plate and alter one tiny region. In a modern detector, it might trigger a small electrical signal at one particular location. Its electric charge was transferred as a complete amount. The detector did not record a faint fraction of the electron smeared evenly across the entire apparatus. This created the same tension that had appeared with light. During propagation, the electron displayed interference and diffraction. During detection, it appeared as a localized impact. The effect becomes especially clear when electrons are sent through an interference experiment one at a time. At first, the detector shows isolated points appearing in apparently unpredictable locations. One electron lands here, another arrives slightly farther away, a third appears elsewhere. There is no faint wave visible on the screen. After many electrons have been detected, however, the distribution of points begins to develop structure. Bright and dark regions gradually emerge. Eventually, the accumulated localized impacts form an interference pattern. Each electron arrives as one event, but the probability of where it arrives follows a wave-like pattern. This cannot be explained by imagining that different electrons simply collide with one another and collectively arrange themselves into fringes. The electrons can be emitted so far apart in time that only one is travelling through the apparatus at once. The pattern still develops. Nor can the result generally be reproduced by assuming that each electron is an ordinary classical particle, secretly choosing one definite path, while the experimenter merely remains ignorant of that choice. If the electron simply took the first path, or the second path in the classical sense, the probabilities associated with those routes would be added. The result would resemble two overlapping particle distributions. Interference requires something different. The contributions associated with the possible routes must combine as probability amplitudes. These amplitudes carry phase information, allowing them to reinforce in some places and cancel in others. The electron is therefore represented by a quantum state containing coherent contributions associated with different possible paths. Coherence means that the phase relationship between those contributions remains sufficiently well defined for interference to occur. If the paths become distinguishable through a measurement or an interaction with the environment, that coherence can be lost and the interference pattern disappears. This is the point at which the phrase "one thing can be two things" becomes useful, provided it is handled with care. The experiment does not require two independent electrons. One electron has not quietly duplicated itself into two separate classical particles. Instead, one quantum state contains a component associated with one root and another component associated with the alternative root. Those components are not independently detected as two pieces of the original electron. They remain parts of a single state and can later be recombined. Their interaction determines the probabilities for the one localized result that eventually appears. The same principle extends beyond electrons. Neutrons, atoms, and molecules have all displayed wave-like interference under suitable conditions. As the mass and complexity of the system increase, the associated wavelength becomes smaller, and environmental isolation becomes more difficult, but the underlying quantum principle remains. Matter, therefore, did not lose its particle-like character when it acquired a wave. Rather, the categories themselves were revealed to be incomplete. An electron is not merely a classical particle that occasionally behaves strangely. It is a quantum system whose state evolves through amplitudes capable of spreading and interfering, while interactions produce definite, localized records. The apparent two paths belong to one state. The single impact belongs to one measurement. Between those two descriptions lies the quiet strangeness of quantum superposition. The wave-like behavior of matter presented physicists with a difficult question. If an electron could spread, diffract, and interfere, what exactly was doing the waving? It could not be an ordinary ripple of material in the same sense as water moving across a pond. An electron was still detected as a complete localized event. Its electric charge did not arrive in several diluted portions across a screen. Yet the pattern of possible detection locations behaved as though something extended through space and combined with itself. In 1926, Erwin Schrödinger developed an equation that gave this strange behavior a precise mathematical form. The Schrödinger equation describes how the quantum state of a system changes through time. It plays a role in quantum mechanics somewhat comparable to the role of Isaac Newton's laws in classical mechanics. Newton's equations describe how positions and velocities evolve under the influence of forces. The Schrödinger equation describes how a quantum state evolves under the influence of the system's energy and surroundings. The central mathematical object in this description is called the wave function. A wave function represents the quantum state of a physical system. Depending on the situation, it can contain information connected with position, momentum, energy, spin, polarization, and other measurable properties. For a single particle moving through space, the wave function can assign a value to every possible location where that particle might later be detected. These values are not ordinary probabilities, they are probability amplitudes. That distinction is essential. An ordinary probability is a positive number describing how likely an event is to occur. A probability of 1/2, for example, represents an equal chance between two alternatives. Probabilities can be added when the alternatives are mutually exclusive, but they do not normally cancel one another. Probability amplitudes behave differently. They can possess positive, negative, or complex phase relationships. The word complex here has a mathematical meaning. It refers to numbers that include a component involving the square root of -1. These numbers may sound rather exotic, but they provide a compact and reliable way to describe both the size and phase of a quantum amplitude. The amplitude itself is not directly observed. To obtain the probability of a possible measurement result, quantum mechanics uses the rule introduced by the German physicist Max Born. The Born rule can be stated as the probability of an outcome is determined by the squared magnitude of its probability amplitude. The squared magnitude always produces a non-negative result, allowing it to function as an ordinary probability. If the wave function assigns a large amplitude to a particular location, the particle is more likely to be detected there. If the amplitude is 0, that outcome will not occur under the conditions being described. This interpretation explains how an extended quantum state can produce localized detections. The wave function may assign amplitudes across many possible positions, but each measurement records one result. When the experiment is repeated many times with the same preparation, the distribution of those results follows the probabilities calculated from the wave function. The wave function should not usually be imagined as a thin cloud of physical matter spread through ordinary three-dimensional space. A water wave consists of water moving. A sound wave consists of changing pressure in a material such as air. An electromagnetic wave consists of changing electric and magnetic fields. The wave function is more abstract. It is a mathematical representation of the quantum state and of the amplitudes associated with possible outcomes. For a single particle, it can sometimes be pictured as a wave extending through space, but this image becomes less straightforward when several particles are involved. A combined system of many particles is described in a higher dimensional configuration space rather than by one ordinary wave floating around the room. Its abstract nature does not make it optional or unreal in its consequences. The wave function predicts interference patterns, atomic energy levels, chemical bonds, tunneling, and countless other measurable effects with extraordinary precision. One of the most important features of the Schrödinger equation is its linearity. Linearity means that if one wave function is a valid possible state, and another wave function is also valid, then an appropriate combination of the two is another valid quantum state. This mathematical property forms the basis of the quantum superposition principle. Imagine a system with two distinguishable possibilities. They might be two paths through an apparatus, two energy levels within an atom, or two possible spin results along a chosen direction. A general quantum state can contain one amplitude for the first possibility and another amplitude for the second. These amplitudes specify the relative weight and phase of each component within the complete state. They must also be normalized. Normalization means adjusting the amplitudes so that the probabilities of all mutually exclusive possible outcomes add to certainty. If only two measurement outcomes are available, the probability of the first plus the probability of the second must equal 1. This does not require the two possibilities to be equally likely. One component may have a much greater amplitude than the other. Superposition means that both contribute coherently to the state, not that nature always divides its attention evenly. The relative phase between the components is just as important as their individual sizes. Two superpositions can assign exactly the same separate probabilities to two alternatives while possessing different relative phases. Those phase differences may remain invisible if the alternatives are measured directly. Yet when the components are recombined, the phase determines how they interfere. With one relative phase, the amplitudes may reinforce one another and produce constructive interference. With another, they may oppose one another and create destructive interference. An outcome that was highly likely can become unlikely, while another may disappear entirely from the final pattern. This is why a superposition cannot be replaced by a simple list of probabilities. The amplitudes contain phase information that ordinary probabilities do not preserve. That hidden relationship determines what happens when possible roots or states are brought back together. The wave function, therefore, describes more than uncertainty about an answer that already exists. It provides the complete quantum state used to calculate how the system evolves and how its alternatives can interfere. Quantum superposition is not merely a poetic way of saying that nature has not made up its mind. It is a precise consequence of linear mathematics. Several amplitudes can belong to one state, evolve together, acquire different phases, and later combine to shape the probabilities of definite measurements. The language may sound like possibility, but the interference it produces is entirely real. A quantum superposition is a single physical state formed from a coherent combination of two or more possible states belonging to the same system. That definition is precise, but it can sound as though several separate realities have simply been piled together. In practice, a superposition is not a loose collection of ordinary conditions. It is one complete quantum state whose components possess definite mathematical relationships to one another. Those components depend on what property is being considered. A particle may be in a superposition of different positions, different paths, different energy levels, or different spin states. A photon may be in a superposition of different polarizations. An atom may contain amplitudes associated with two allowed energies. The phrase superposition, therefore, does not identify one particular kind of physical arrangement. It describes a general structure that can apply to many different measurable properties. These measurable properties are called observables. Position is an observable. Energy is an observable. Momentum, spin, polarization, and path can also function as observables in appropriate experiments. Each observable comes with a set of possible measurement outcomes, and a quantum state can be described in relation to those outcomes. To see why this matters, consider the polarization of a photon. Polarization describes the orientation associated with the photon's electromagnetic behavior. A measuring device might be arranged to distinguish horizontal polarization from vertical polarization. If a horizontally polarized photon enters the device, it produces the horizontal result with certainty. If a vertically polarized photon enters, it produces the vertical result with certainty. Now imagine a photon prepared with diagonal polarization. Relative to a horizontal and vertical measuring arrangement, the diagonally polarized photon can be expressed as a superposition of horizontal and vertical polarization. It contains one probability amplitude associated with the horizontal outcome and another associated with the vertical outcome. When measured in that basis, the detector records one result or the other. The photon is not recorded as a faint half horizontal and half vertical smudge. Yet before the measurement, its state is not correctly described as secretly horizontal or secretly vertical. This introduces the idea of a basis. A basis is a chosen set of mutually distinguishable states used to describe a quantum system and the outcomes available in a particular measurement. Horizontal and vertical polarization form one possible basis. Two opposite diagonal polarizations form another. The choice of basis is closely connected to the physical orientation of the measuring apparatus. Changing the apparatus changes the question being asked of the photon. A diagonally polarized photon is a superposition when described in the horizontal and vertical basis. However, in the diagonal basis, that same photon may be one definite basis state. Nothing physical about the photon needs to change merely because the mathematical description has changed. The difference lies in which measurement outcomes are being used to describe it. This means that asking whether a particle is really in a superposition is incomplete. A more precise question would ask which property is being considered and relative to which basis. An electron may have a definite spin state along one direction, while being in a superposition of spin outcomes along another. An atom may have a definite energy, but a spread of possible positions. A photon may possess definite diagonal polarization, while appearing as a superposition of horizontal and vertical polarizations. Superposition is therefore basis dependent. A simple geographical analogy can help. Imagine an arrow pointing northeast. It is not uncertain about its direction. It points northeast quite definitely. Yet that direction can be decomposed into a northern component and an eastern component. Relative to north and east, the northeast direction contains both. It would be misleading to say that the arrow is secretly pointing only north or only east. It has one definite direction that can be expressed through two components in a chosen coordinate system. Quantum states share something with this idea. A definite state in one basis can be represented as a combination of states in another basis. The comparison has limits, however. Ordinary directional components do not reproduce the full behavior of quantum probability amplitudes. Quantum amplitudes carry phase relationships and determine probabilities through the Born rule. They can interfere constructively or destructively when components are recombined. A classical arrow does not produce different probabilities merely because its components acquire a relative phase. Quantum superpositions do. This phase relationship is central to coherence. A coherent superposition is one in which the relative phase between its components remains well defined. The components are not merely present with certain weights, they are linked by a stable relationship that determines how they will combine during a later experiment. If two path amplitudes remain coherent, they can interfere. Where their phases align, they may reinforce one another. Where they oppose, they may cancel. That interference is what separates a genuine quantum superposition from a classical statistical mixture. Imagine a source that produces horizontally polarized photons half the time and vertically polarized photons half the time. Unless someone keeps a record, an observer may not know which type has been emitted in any individual trial. This is a mixture. Each photon is already in one state or the other, while the observer has incomplete information about which one. Now imagine a source that prepares every photon in the same diagonal polarization. In the horizontal and vertical basis, each photon is in a coherent superposition of those two states. A direct measurement in the horizontal and vertical basis may produce the same apparent statistics in both cases. Half of the detections might be horizontal and half vertical. Looking only at that one set of results could make the mixture and the superposition seem identical. A different measurement can reveal the distinction. If the photons are measured in the diagonal basis, the coherently prepared photons can all produce the same diagonal result. Their horizontal and vertical amplitudes recombine with the phase relationship required to restore the definite diagonal state. The mixed photons behave differently. Because each is actually horizontal or vertical, and because there is no stable phase relationship between the alternatives across the collection, the same recombination does not produce a single definite diagonal outcome. Interference therefore provides an operational way to distinguish a coherent superposition from ordinary uncertainty. A superposition preserves phase information. A mixture does not. This distinction also explains why environmental interactions are so important. If the surroundings acquire information that distinguishes the components, the stable phase relationship becomes inaccessible. Coherence is lost, and the system begins to behave like a statistical mixture for practical measurements. A quantum system in superposition is not several unrelated classical systems stacked together. It is one state with several components connected through amplitudes and phase. The parts of the mathematical description matter because of how they combine. Remove the coherence and the characteristic interference disappears. Preserve it, and the different possibilities can work together to shape outcomes that no classical mixture can reproduce. So a superposition is not merely a list of things that might happen. It is a structured quantum state. Its components depend on the property being measured, the basis used to describe it, and the phase relationships that hold those components together. The system remains one thing. It is the possibilities within its state that are many. The double-slit experiment provides one of the clearest ways to see what path superposition actually means. Imagine a source aimed toward a barrier containing two narrow openings. Beyond the barrier sits a detector capable of recording where each arriving particle lands. The particles may be photons of light or electrons, and the source can be adjusted so that they are emitted individually. One particle leaves the source. It approaches the barrier, passes through the experimental arrangement, and eventually produces one small mark on the detector. Then another particle is released. It also creates one localized mark. At first, the points may appear scattered and irregular. Nothing about the first few detections looks especially wave-like. Each event seems compact and particle-like, exactly as ordinary intuition might expect. But as the process continues, a larger pattern slowly emerges. Some regions of the detector receive many impacts. Other regions receive far fewer. After enough particles have arrived, the accumulated points form alternating bands of high and low intensity. An interference pattern appears. The experiment therefore presents two behaviors at once. Every individual detection is localized, yet the overall distribution follows the structure expected from interfering waves. Sending the particles one at a time makes the result especially important. If a dense stream of electrons were traveling through the apparatus, It might be tempting to imagine that the particles were bumping into one another, exchanging forces and somehow organizing themselves into the pattern. But the experiment can be performed with enough time between emissions that only one particle is present in the apparatus at any moment. The next electron may not be released until the previous one has already reached the detector. There is no second electron nearby with which the first can collide. Yet after many separate trials, the interference pattern still develops. The pattern must therefore arise from the way each individual quantum state evolves through the apparatus. When both slits are open and no physical interaction distinguishes the routes, the particle is described by a state containing two path amplitudes. One amplitude is associated with the possibility of travelling through the first slit. The other is associated with the possibility of travelling through the second. These are not ordinary probabilities stating that the particle has a certain chance of secretly taking one route and a certain chance of secretly taking the other. They are probability amplitudes, and amplitudes can combine before probabilities are calculated. At every possible point on the detector, the contribution associated with the first slit is added to the contribution associated with the second slit. The central rule can be stated as the total amplitude is found by adding the amplitudes for all indistinguishable alternatives, and the probability is obtained from the squared magnitude of that total. This order matters. First, the amplitudes are added. Only afterward is the probability calculated. Where the two amplitudes arrive with matching phases, they reinforce one another. The total amplitude becomes larger, producing a greater probability of detection. These regions develop into bright or densely populated bands. Where the amplitudes arrive with opposing phases, they partially or completely cancel. The total amplitude becomes smaller, sometimes reaching zero. Those regions produce dark bands or areas with very few detections. This is constructive and destructive interference expressed through quantum probability amplitudes. If the experiment involved only ordinary uncertainty about a definite classical route, the calculation would be different. The probability for a particle travelling through the first slit would simply be added to the probability for a particle travelling through the second. Ordinary probabilities do not carry the same phase relationship. They do not usually cancel one another. Adding them would produce two overlapping distributions rather than the alternating bright and dark fringes observed in the experiment. The mathematical difference appears through what are often called interference terms. When amplitudes are added and the squared magnitude of the total is calculated, additional contributions arise from the relationship between the two amplitudes. Those contributions can be positive or negative, creating the fringes. They are absent when only separate classical probabilities are added. This is why the interference pattern reveals more than incomplete knowledge. It shows that the two alternatives remain coherent parts of one quantum state. The particle should not be pictured as physically tearing itself into two smaller fragments at the barrier. An electron does not divide its electric charge into two half electrons, each carrying one portion through a different opening. When detection occurs, the detector receives the full elementary charge of one electron at one location. A photon behaves similarly. It does not ordinarily deposit half of its energy in one bright band and the other half somewhere else. A single detection transfers one full quantum of energy associated with the photon's frequency. The state can spread across possible paths, but the recorded event remains whole and localized. This creates a delicate distinction. The quantum description contains two coherent path components, yet the measurement does not reveal two pieces of the particle. One complete outcome appears. Richard Feynman developed a particularly powerful way of expressing this structure through the sum over history's formulation of quantum mechanics. In this approach, an amplitude is associated not merely with one classical route, but with every physically possible path connecting the initial and final conditions. These path amplitudes carry phases and are added together. Most contributions cancel extensively, while groups of nearby paths can reinforce one another. For the double-slit arrangement, the important alternatives can be grouped into paths passing through the first opening and paths passing through the second. Their combined contributions determine the probability of detection at each point on the screen. Feynman's language can sound as though the particle literally explores every imaginable road. It is safer to treat the alternative paths as part of the mathematical calculation used to predict measurable results. The experimentally secure fact is that the amplitudes associated with indistinguishable alternatives must be combined, and their interference determines the observed distribution. This brings us to the natural question of which slit the particle really passed through. The question assumes that the electron possessed one definite classical trajectory all along, whether or not anyone observed it. But the unmeasured experiment does not reveal such a path. Instead, it produces a pattern that depends on both root amplitudes remaining coherent. Treating one slit as the hidden true root and the other as merely unreal does not reproduce the full interference without adding some further non-classical structure. Quantum mechanics therefore answers a different question. It predicts the probabilities for possible outcomes from the complete state prepared by the apparatus. When both paths are available and indistinguishable, the state includes both contributions. When a detector records the final position, one localized result appears. The phrase "one particle taking two paths" is useful only if it is understood carefully. There are not two independent particles, and there are not two separately observed journeys. There is one quantum system described by two coherent alternatives. Those alternatives can separate, acquire different phases, and later recombine. Their interference shapes whether one final detection is likely to occur. This is the most direct physical meaning of path superposition. One thing is not duplicated into two ordinary things. One quantum state contains two possible routes, and both remain relevant until the experiment makes them distinguishable or produces a definite result. The double-slit experiment changes dramatically when the two available paths can be distinguished. With both slits open and no path information available, the probability amplitudes associated with the two routes combine. In some places they reinforce one another, in others they cancel. Over many repeated detections, those differences create the familiar pattern of bright and dark fringes. But when the experiment is modified so that the path of each particle can, even in principle, be identified, the interference pattern fades or disappears. The important point is that no human being needs to read the result. The information does not have to appear on a screen, enter someone's eyes, or be consciously understood. It only has to become physically stored in some distinguishable form. A which path measurement is therefore not defined by human knowledge alone. It is a physical interaction that correlates the route taken by the particle with another system. That other system might be a detector placed near the slits. It could be a photon scattered from the moving particle. It might be an atom whose internal state changes differently depending on the path. It could even be part of the surrounding environment. Suppose an electron approaches two slits. If it passes through the first slit, a nearby detector changes into one state. If it passes through the second slit, the detector changes into another distinguishable state. The combined quantum state now contains two correlated alternatives. One connects the first path with the first detector state. The other connects the second path with the second detector state. This kind of correlation is called quantum entanglement. Entanglement means that the complete state cannot be separated into one independent state for the electron and another independent state for the detector. The path of the electron and the condition of the detector must be described together. The first path is linked with one record. The second path is linked with another. Once those detector states are physically distinguishable, the path alternatives no longer combine in the same way when only the electron is examined. The phase relationship has not necessarily vanished from the total combined state, but it has become distributed across the electron and the apparatus. The electron's two path amplitudes are now tied to different environmental records. Because those records distinguish the alternatives, the simple interference pattern disappears, This does not happen because the detector has kicked the particle in some crude mechanical way, although physical disturbance can certainly matter in some experiments. Even a carefully designed interaction can remove interference if it leaves behind reliable path information. The decisive issue is distinguishability. If the surroundings contain a record that tells the two routes apart, the alternatives no longer function as indistinguishable contributions to the same final outcome. This is why the phrase observation can be misleading in quantum mechanics. It may suggest that consciousness has some special power to force reality into one form. In ordinary laboratory physics, no such assumption is needed. A detector can record a path overnight in an empty room. The interference pattern will still be lost. A file containing the result can remain unopened forever. The physical correlation already exists. The universe does not wait for someone to check the paperwork. Niels Bohr described the relationship between interference and path information through the principle of complementarity. Complementarity states that certain kinds of experimental information require mutually exclusive arrangements. A setup designed to reveal wave-like interference cannot simultaneously provide complete particle-like path information. This is not simply a weakness in the equipment, it reflects the structure of quantum measurement. To observe a full interference pattern, the alternatives must remain indistinguishable. To determine the path precisely, the experiment must create a physical difference between those alternatives. The more clearly the path can be identified, the less visible the interference fringes become. This trade-off can be measured quantitatively. If path distinguishability is very low, the fringe pattern can possess high visibility, with strong bright bands and deep dark gaps. As path information becomes more reliable, the contrast of the fringes decreases. Partial path information produces partial interference. The change is not always an abrupt switch from a perfect pattern to no pattern at all. Experiments can occupy intermediate conditions in which the two routes are somewhat distinguishable, and the fringes remain visible but weakened. This reveals that wave-like interference and particle-like path knowledge form a continuous balance. A particularly subtle version of this idea appears in quantum eraser experiments. In such experiments, the path of a particle becomes correlated with another property or another particle. The path information may be encoded, for example, in different polarizations. If those polarization states are distinguishable, the ordinary interference pattern disappears when all detections are considered together. However, the associated information can later be measured in a different basis, one that does not reveal which path was taken. When the results are sorted according to those correlated measurements, interference patterns can reappear within selected subsets of the data. This is often described as erasing the path information. The phrase can make the process sound more dramatic than it is. Nothing needs to be physically rubbed out after the particle has arrived. Instead, the experiment is arranged so that the relevant measurement no longer distinguishes the path alternatives. Different correlations are revealed depending on how the companion system is measured. One selected group of detections may form an interference pattern. Another group may form a complementary pattern shifted in the opposite direction. When all groups are combined without sorting, the patterns overlap and cancel, leaving no visible fringes. Quantum eraser experiments are sometimes said to alter the past, especially when the choice of measurement occurs after the first particle has already been detected. That description is misleading. The later choice does not travel backward through time and force the particle to revise an earlier journey. The original unsorted detections never display a usable interference pattern by themselves. The later measurement determines how correlated results are grouped and which statistical relationships become visible. No information is sent into the past and no settled event is rewritten. What changes is the way the combined data are organized according to the entangled correlations present in the experiment. The disappearance of interference is therefore part of a broader transition. A coherent superposition begins with alternatives that retain a stable phase relationship and remain capable of combining. When information about those alternatives spreads into a detector or the environment, they become effectively separate possibilities. For practical purposes, they begin to resemble classical alternatives. One path becomes associated with one record. the other becomes associated with another. The delicate relationship that allowed direct interference is no longer accessible through measurements of the particle alone. This is one of the first steps toward decoherence in the classical world. The lesson is not that knowledge mysteriously changes reality. It is that information must always exist physically. A path record is stored in matter, radiation, motion, or some other measurable degree of freedom. When that physical information distinguishes the alternatives, interference is reduced. When the alternatives remain indistinguishable and coherent, they can still combine. Human awareness is not the deciding factor. The decisive question is whether the world itself has acquired a physical record of which path was taken. Quantum superposition does not require a particle to travel through two separate regions of space. It can also appear within properties that have no direct classical equivalent. One of the clearest examples is quantum spin. Spin is an intrinsic form of angular momentum possessed by particles such as electrons, protons, and neutrons. Angular momentum is usually associated with rotation. A spinning wheel has angular momentum, as does a planet turning around its axis. The faster it rotates and the more its mass is distributed away from the centre, the greater that angular momentum becomes. The word spin was borrowed because quantum particles respond to magnetic fields and obey conservation laws in ways that resemble objects carrying angular momentum. Yet an electron should not be imagined as a tiny solid sphere physically rotating around an internal axis. That picture quickly produces problems. As far as experiments can determine, the electron behaves as an elementary particle with no measurable internal size or structure. If its spin were caused by the surface of a small charged sphere rotating rapidly enough to reproduce the observed magnetic properties, parts of that surface would have to move in ways that are incompatible with relativity. Electron spin is therefore not ordinary mechanical rotation. It is an intrinsic quantum property built into the identity of the particle itself. A famous experiment performed in 1922 revealed just how unlike classical rotation this property could be. Otto Stern and Walter Gerlach sent a beam of silver atoms through a non-uniform magnetic field. Silver atoms were useful because their overall magnetic behavior was largely determined by one unpaired electron. A magnetic object passing through a varying magnetic field experiences a force whose direction and strength depend on its magnetic orientation. If the atoms behaved like tiny classical magnets pointing in random directions, the beam should have spread into a continuous band. Every possible orientation would have produced a slightly different deflection. Instead, the beam separated into distinct parts. In the original Stern and Gerlach experiment, the silver atoms formed two clearly separated traces. The magnetic behavior was quantized. Along the chosen measurement direction, the relevant spin component did not take every possible value. It produced one of two discrete outcomes. These outcomes are commonly called spin up and spin down. The words up and down do not mean that the electron itself is literally pointing upward or downward, like a miniature compass needle. They label the two results available when a spin 1/2 particle is measured along a selected direction. The direction of measurement matters. An apparatus may be aligned vertically, horizontally, or along some other axis. Each orientation asks a different physical question about the particle's spin. Suppose an electron is prepared so that its spin is definitely up along the vertical direction. If it is immediately measured again along that same direction, it will produce the up result with certainty. However, if the same electron is measured along a horizontal direction, quantum mechanics does not assign it one definite horizontal spin value in advance. Relative to the horizontal basis, the vertically prepared state is a superposition of horizontal spin up and horizontal spin down. One state that is definite for a vertical measurement therefore becomes a coherent combination of possibilities for a horizontal measurement. This is basis dependence in a particularly clean form. The electron has not become vague in every possible sense. Its vertical spin was prepared precisely. The uncertainty appears because a different component of spin is being measured. A sequence of Stern and Gerlach type experiments makes the effect even clearer. Imagine sending atoms through a device aligned vertically. The beam separates into vertical spin-up and vertical spin-down. The vertical spin-up beam is selected while the other is blocked. Every atom in the surviving beam is now prepared in the same definite vertical spin state. If that beam passes through a second device also aligned vertically, it remains in one branch. The same result is obtained again. Now place the second device horizontally instead. The vertically prepared atoms divide into two horizontal outcomes. Roughly half are measured as horizontal spin-up and half as horizontal spin-down. Select only the horizontal spin-up atoms and send them through a third device aligned vertically once more. Classical intuition might suggest that the atom should remember their original vertical preparation, yet the beam splits again into vertical spin-up and vertical spin-down. The intermediate horizontal measurement changed the quantum state. After the particle was prepared as definite horizontal spin-up, it became a superposition of the two vertical spin outcomes. The original certainty had been replaced by renewed uncertainty. This does not mean that the measuring apparatus merely uncovered values that were sitting quietly inside the particle all along. The pattern of successive measurements shows that the different spin components cannot all be assigned ordinary definite values in the classical way. Preparing a definite answer to one question changes the possible answers to another. Spin therefore demonstrates that superposition is not simply a matter of a particle occupying two places or passing through two slits. The alternatives may concern an internal quantum property rather than separate routes through space. A useful geometric picture for a two-state quantum system is the Bloch sphere. The north and south poles of the Bloch sphere can represent two chosen basis states, such as spin up and spin down along one direction. Every point on the surface represents a possible pure superposition of those basis states, including different relative amplitudes and phases. States near the North Pole are weighted more strongly toward one basis result. States near the South Pole favour the other. Points around the equator represent equal weight superpositions with different relative phases. The Bloch sphere is a mathematical representation, not a tiny globe hidden inside the particle. The electron does not contain a physical arrow secretly pointing to a location on that sphere. The geometry provides an elegant way to organise the possible states and predict how they respond to measurements and controlled interactions. This same two-state structure forms the basis of a quantum bit. A classical bit has one of two definite values. A quantum bit can occupy any coherent superposition of two chosen basis states. The relative amplitudes determine the probabilities of the two outcomes, while the relative phase affects how the state interferes during later operations. An electron spin can serve as a quantum bit. So can a photon's polarization, two energy levels of an atom, or two states of a superconducting circuit. Although the possible superpositions form a continuous range, each measurement still produces a discrete result. A spin measurement along a chosen axis gives spin up or spin down. It does not return a softly blended answer somewhere between them. This contrast is central to quantum mechanics. The state can vary continuously through different amplitudes and phases, while the observed outcomes remain quantized. Spin also reveals why saying that a particle is either definite or in superposition is too simple. The same state may be definite relative to one measurement basis and a superposition relative to another. The electron can therefore carry a perfectly definite answer to one carefully chosen question, while appearing as a combination of alternatives when the apparatus asks something different. Quantum superposition is not always about being here and there. Sometimes it is about how one complete state contains several possible answers, depending on the direction from which nature is questioned. An atom is often pictured as a tiny solar system, with electrons circling a central nucleus as planets circle the sun. It is a memorable image, but modern quantum mechanics describes something considerably stranger. Electrons inside atoms do not travel along ordinary fixed orbits. Instead, they occupy quantum states represented by wavefunctions. These states form patterns called atomic orbitals, which describe the probability distributions and other measurable properties associated with the electrons. Only certain atomic energies are allowed. An electron bound to a nucleus cannot normally possess just any energy it happens to prefer. It must occupy one of a set of discrete energy levels determined by quantum mechanics, the electric attraction between the negatively charged electron and the positively charged nucleus, and the interactions among electrons when more than one is present. This quantization explains why atoms absorb and emit light at characteristic frequencies. An electron can move between allowed states when the atom gains or loses an amount of energy matching the difference between those levels. Niels Bohr introduced an important early version of this idea in 1913. In the Bohr model, electrons occupied certain permitted circular orbits around the nucleus and moved between them by absorbing or emitting specific quantities of energy. The model successfully explained several features of hydrogen, including the regular pattern of frequencies in its spectrum. Yet it could not fully describe more complicated atoms, chemical bonding, or the detailed behavior revealed by later experiments. Modern quantum mechanics replaced Bohr's fixed paths with wave functions and orbitals. The energy levels remained, but the electrons were no longer treated as tiny planets following precise tracks. An atom can occupy one definite energy state, but it can also be prepared in a coherent superposition of two different energy states. This may be achieved using carefully controlled electromagnetic radiation. A pulse of radio waves, microwaves, or light can interact with the atom for a precisely chosen duration. If the frequency and timing are correct, the pulse does not necessarily transfer the atom completely from the lower state to the higher one. Instead, it can create a quantum state containing an amplitude for each. The atom is then described by one coherent combination of two energy possibilities. This does not mean that the atom contains two independent copies of itself, one carrying each energy. Nor does it simply mean that the atom secretly occupies one level, while the experimenter remains uncertain. The two components possess a controlled relative phase and can later interfere. Once the superposition has been prepared, its components evolve differently through time. Each energy state accumulates phase at a rate determined by its energy. Because the two components have different energies, their relative phase steadily changes. The rate of this change is directly related to the energy difference between them. That evolving phase can be measured with extraordinary precision. Atomic clocks are among the most impressive applications of this principle. They do not work by watching electrons orbit a nucleus like hands moving around a miniature clock face. Instead, they use extremely stable quantum transitions between carefully selected atomic energy states. Cesium atomic clocks use two closely spaced states within the ground state hyperfine structure of cesium-133. Hyperfine structure arises from the interaction between the magnetic properties associated with the electrons and the atomic nucleus. The energy difference between the two selected cesium states corresponds to microwave radiation at a remarkably stable frequency. The second is defined through this transition. 1 second is the duration of 9,192,631,770 periods of the radiation associated with the transition between those two hyperfine levels of the ground state of cesium-133. The number is rather less relaxing than the clock itself, but its precision is the point. To measure this frequency accurately, atomic clocks make use of coherent superpositions and interference. Norman Ramsey developed the method of separated oscillatory fields, building upon earlier work by Isidor Isaac Rabi. Instead of exposing atoms to one long interaction, Ramsey's method applies two shorter electromagnetic pulses separated by a period of free evolution. The first pulse prepares each atom in a superposition of the two selected energy states. During the interval between pulses, the two components accumulate different phases because of their energy difference. The second pulse recombines the components. The probability of finding the atom in either energy state depends on the relative phase acquired during the waiting period. If the applied microwave frequency matches the natural transition frequency precisely, the interference produces a characteristic response. If it is slightly too high or too low, the phase relationship shifts and the measured populations change. By adjusting the microwave source until the atomic response reaches the correct interference condition, the clock locks its output to the natural transition frequency of the atoms. This technique is called Ramsey interference. It allows extremely small frequency differences to be measured, because even a slight mismatch accumulates into a detectable phase shift over time. Related behavior appears in Rabi oscillations, named after Isidor Isaac Rabi. When a two-level quantum system is continuously driven by electromagnetic radiation close to its transition frequency, the probability of finding it in the lower or higher state can oscillate rhythmically. The atom moves through a sequence of superpositions as the state evolves. At one moment, the atom may be found almost certainly in the lower state. Later, the population may shift strongly toward the upper state. Between those moments, the state contains coherent contributions from both. The rate of this oscillation depends on the strength of the driving field and how closely its frequency matches the atomic transition. These effects allow physicists to prepare, rotate, and read quantum states with great control. It would be misleading, however, to imagine that an atom in an energy superposition is simply radiating half of one color and half of another. The observable behavior depends on the full quantum state, including the amplitudes, the relative phase, the interaction with the measuring device, and the basis in which the measurement is performed. A direct energy measurement produces one allowed energy result. Interference becomes visible when the components are deliberately recombined in a way that makes their relative phase measurable. This ability lies at the heart of spectroscopy. Spectroscopy studies how matter absorbs, emits, and responds to electromagnetic radiation. By measuring resonant frequencies, physicists can determine energy differences within atoms and molecules. Tiny shifts reveal magnetic fields, electric fields, motion, chemical surroundings, gravitational effects, and interactions with other particles. Coherent superpositions make these measurements especially sensitive. A weak influence may slightly change the relative phase between two energy components. After enough time, that small phase difference can be converted into a measurable change in the probabilities of the final outcomes. The same principle supports magnetic resonance, quantum sensing, precision navigation, and laboratory tests of fundamental physics. Atomic interferometers can search for tiny variations in forces. Trapped ions and neutral atoms can serve as quantum bits. Highly accurate clocks can compare the passage of time at slightly different heights, revealing gravitational time dilation across surprisingly small vertical distances. Energy superposition is therefore not merely a strange interpretation of what an atom might be doing before someone looks. It is a controllable physical resource. Scientists can prepare the components, allow them to evolve, shift their phases, recombine them, and measure the resulting interference. The process is repeatable, quantitative, and useful. An atom can contain more than one energy possibility within a single coherent state. Yet every direct energy measurement still produces one definite level. Between preparation and measurement, the relative phase quietly keeps time, and with the right experiment, that hidden rhythm becomes one of the most precise tools humanity has ever created. Quantum mechanics describes a world of possibilities with extraordinary precision. A wavefunction can contain several coherent components, each associated with a different possible result. Under the Schrödinger equation, those components evolve smoothly through time, changing their phases and interfering according to clear mathematical rules. Then a measurement occurs and only one outcome appears. A detector does not record a soft blend of all the available possibilities. It produces one click, one flash, one electrical pulse, or one permanent mark. The smooth evolution of many amplitudes seems to give way to a single definite event. The tension between those two descriptions is known as the measurement problem. According to the Schrödinger equation, a quantum state normally develops continuously and predictably. If the state begins as a superposition, the equation preserves that superposition as it evolves. Each component changes according to the energy and interactions of the system, but the mathematics does not naturally select one component and erase the rest. Textbook quantum mechanics therefore introduces an additional rule for measurement. This is often called the projection rule, or the collapse of the wave function. When an observable is measured, the quantum state is said to collapse into one of the allowed states associated with the possible results. Which outcome appears cannot generally be predicted in advance, but the probability of each result is determined by the Born rule. The Born rule states that the probability of an outcome is determined by the squared magnitude of its probability amplitude. Before measurement, the state may contain several amplitudes. After measurement, the description is updated to the state corresponding to the result that was actually recorded. Consider an electron approaching a position-sensitive detector. Its wave function may be spread across a wide region, assigning probability amplitudes to many possible points of arrival. Those amplitudes may have passed through different routes and interfered before reaching the detector. Yet the detector does not report that the electron arrived weakly across the whole screen. It registers one localized event. In a photographic plate, the electron might alter one tiny patch of material. In a semiconductor detector, it may produce a local electrical pulse. In another apparatus, the event could generate a flash of light that is amplified and stored electronically. The initial distinction may involve the position of a single microscopic particle. The final record may involve millions or billions of atoms, an electrical current, a digital file, and a visible mark on a screen. Measurement is therefore a physical process of amplification. A small quantum difference becomes connected to a large and stable macroscopic difference. An electron arriving here activates one region of the detector. An electron arriving there activates another. Those alternatives are magnified until they can be copied, stored, compared, and communicated. No conscious observer is required for this to happen. An automated detector can operate in a sealed laboratory while everyone is asleep. The data can be recorded and left unread for months. The physical interaction has already created a durable record. The detector is not waiting politely for a human mind to arrive and complete the experiment. Quantum mechanics predicts the distribution of such records with remarkable accuracy. It may calculate that one region of the detector will receive 10% of the events, another region 30%, and a third region 60%. If the same quantum state is prepared and measured many times, the observed frequencies approach those predicted probabilities. The overall pattern is stable and reproducible. The location of any one electron, however, cannot generally be predicted with certainty. Quantum theory provides the probability distribution, but not the specific result of an individual trial. This distinction is crucial. The statistics can be precisely predictable, even when the individual event is not. A laboratory can repeat the same preparation thousands or millions of times and obtain an extremely reliable distribution. Yet before each detection, standard quantum mechanics usually offers only probabilities for where the next event will occur. The theory is therefore not simply vague. It predicts randomness in a highly structured way. John von Neumann gave one of the most influential formal accounts of quantum measurement during the early 20th century. He treated the measured system and the apparatus within a shared mathematical framework. Suppose a particle begins in a superposition of two possible states. The apparatus begins in a neutral condition, ready to measure. During the interaction, the first particle state becomes correlated with one apparatus state, while the second particle state becomes correlated with another. The system and detector become entangled. The combined state now contains one component linking the first result to one detector record and another component linking the second result to a different record. If the Schrödinger equation is applied consistently, This entangled state can continue to expand. The detector becomes correlated with the surrounding environment. A computer stores the reading. A person later sees the result. Each stage can be included in a larger quantum description. This creates what is sometimes called the von Neumann chain. The microscopic system becomes correlated with the apparatus. The apparatus becomes correlated with the environment. The observer becomes correlated with the recorded outcome. But where within this chain does one definite result finally appear? The projection rule says that one outcome is selected. It provides the correct probabilities and allows calculations to proceed. What remains uncertain is what that collapse means physically. One possibility is that collapse is a real event. The wave function may genuinely change in a sudden and non-unitary way, removing all but one outcome. Another possibility is that collapse represents an update of information. Once a result is known, the observer changes the mathematical state used to describe the system, much as probabilities are updated after new evidence becomes available. A further view is that collapse is an effective description. Interaction with the environment causes decoherence, making the different outcomes behave as though they have separated into classical alternatives, even if the total quantum state has not fundamentally collapsed. In interpretations such as the many worlds interpretation, there is no unique physical collapse. The combined state continues to contain multiple effectively separate branches, while each observer becomes correlated with one definite record within a particular branch. Objective collapse theories take a different route and propose new physical mechanisms that cause sufficiently large superpositions to reduce spontaneously. These accounts disagree about reality, but they often agree about the results of ordinary laboratory experiments. Standard quantum mechanics remains one of the most accurately tested frameworks in science. Its predictions for atoms, particles, light, chemistry, electronics, and precision measurements have succeeded across an enormous range of conditions. The argument is not mainly about whether the calculation works. It is about what the successful calculation tells us is happening. Measurement transforms a delicate relationship among probability amplitudes into a robust fact within ordinary experience. Before the interaction, the quantum state may contain coherent possibilities. Afterward, the laboratory contains one recorded mark that can be photographed, copied, and discussed. The other possible outcomes do not appear beside it in the same record. That is the heart of the measurement problem. Quantum theory allows one system to evolve through many possibilities, yet experience presents one result at a time. The mathematics predicts exactly how often each answer should appear. What it does not yet provide, without interpretation or an additional physical rule, is one universally accepted explanation for why this particular answer becomes the reality that is recorded. Erwin Schrödinger's famous cat was never intended to be a cheerful proposal for an afternoon experiment. When Schrödinger introduced the thought experiment in 1935, he was trying to expose a serious problem. Quantum mechanics allowed microscopic systems to exist in superpositions of distinct possibilities. If the same rules were applied without restriction to larger objects, then those possibilities seemed capable of spreading outward, until they included detectors, machines, animals, and perhaps observers themselves. The cat was designed to make that consequence impossible to ignore. Imagine a sealed box containing a cat, a small quantity of radioactive material, a radiation detector, and a mechanism connected to a container of poison. The radioactive material is arranged so that there is some probability that one nucleus will decay during a chosen period of time. If the nucleus decays, the detector responds. The mechanism is triggered, the poison is released, and the cat dies. If no decay occurs, the detector remains silent, the mechanism does nothing, and the cat survives. Radioactive decay is a quantum process. Before a definite outcome is recorded, the nucleus may be represented by a state containing an amplitude for having decayed and another amplitude for remaining undecayed. Quantum theory can therefore describe the nucleus as a superposition of those alternatives. The trouble begins when the nucleus is connected to the rest of the apparatus. the decayed component becomes correlated with a detector that has fired. The undecayed component becomes correlated with a detector that has not fired. The detector is linked to the mechanism, and the mechanism is linked to the condition of the cat. The combined state now contains one alternative in which the nucleus has decayed, the detector has responded, the mechanism is activated, and the cat is dead. It also contains another alternative in which the nucleus is not decayed, the detector remains unchanged, the mechanism is inactive, and the cat is alive. These parts of the combined state are entangled. Entanglement means that the individual systems can no longer be assigned independent pure states. The condition of the nucleus is connected with the condition of the detector. The detector is connected with the mechanism, and the mechanism is connected with the cat. The complete state must be described through those correlations. This is sometimes shortened into the statement that the cat is both alive and dead at the same time. That phrase is memorable, but it is also easy to misunderstand. The formal quantum description is not an ordinary animal occupying a hazy condition halfway between life and death. It is a combined state containing macroscopically different correlated alternatives. One alternative contains a living cat, the other contains a dead cat. The puzzle is that the basic quantum equations appear able to retain both components, until some rule or process explains why only one definite outcome is experienced. Schrödinger was not suggesting that cats could casually be placed into visible superpositions in a real laboratory. He chose an animal precisely because the conclusion seemed absurd when quantum language was extended directly from one radioactive nucleus to an everyday object. The example was a criticism of an incomplete account of measurement. It asked where the quantum possibilities end and the definite classical world begins. The historical context is important. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published an argument questioning whether quantum mechanics provided a complete description of physical reality. Their reasoning involved two systems prepared in a shared quantum state. Measurements on one system allowed predictions about the other, even when the systems were widely separated. They argued that either quantum mechanics was incomplete, or the theory required an unsettling kind of non-local relationship. Schrödinger responded to these discussions and introduced the term entanglement to describe the deep quantum connection between systems whose combined state cannot be separated into independent parts. The cat thought experiment applied the same principle across an enormous difference in scale. A microscopic event becomes entangled with a macroscopic apparatus. The apparatus becomes correlated with the fate of an animal. What began as a superposition involving one nucleus appears to grow into a superposition involving the contents of the entire box. This raises the measurement problem in its sharpest form. If the Schrödinger equation governs every part of the arrangement, then the combined superposition should continue evolving. Yet when the box is opened, nobody reports seeing an obvious interference between a living cat and a dead one. One definite condition is found. It is tempting to say that opening the box causes the change. However, the cat and the apparatus have already undergone countless physical interactions long before a person lifts the lid. The radioactive nucleus interacts with the detector. The detector affects the mechanism. Molecules of air collide with every surface. Thermal radiation is emitted and absorbed. Light scatters through the interior. The cat's body contains an immense number of particles continually interacting with one another. The box may be sealed from the observer, but it is not an empty, perfectly isolated quantum laboratory inside. These interactions lead to decoherence. As information about the alternative spreads into the internal environment, the phase relationship required for observable interference becomes extraordinarily difficult to preserve. The living and dead alternatives become correlated with different states of countless surrounding particles. For all practical measurements, they begin to behave like separate classical possibilities rather than components capable of visibly interfering. Decoherence helps explain why macroscopic superpositions are not observed in everyday life. Large systems interact so strongly with their environments that coherence is lost with remarkable speed. But decoherence does not automatically answer every part of Schrödinger's challenge. It explains why interference between the macroscopically distinct alternatives becomes effectively inaccessible. It explains why the system behaves as though it were a classical mixture of outcomes. What it does not, by itself, provide is one universally accepted explanation for why a particular observer experiences one result rather than the full combined quantum state. Different interpretations answer that question differently. A collapse interpretation says the state reduces to one outcome. An objective collapse theory proposes a genuine physical mechanism that destroys large superpositions. The many-worlds interpretation says both branches remain in the universal wavefunction, while each observer becomes correlated with only one outcome. Other interpretations treat the quantum state as relational, informational, or dependent on the physical context of observation. The cat does not choose among these possibilities. Its purpose is to show that the question cannot be avoided. Schrödinger's cat is therefore not mainly a story about an unfortunate animal existing in two ordinary conditions. It is a precise challenge concerning how microscopic quantum possibilities become macroscopic facts. The radioactive nucleus, detector, mechanism, and cat form one entangled physical system. Quantum theory describes the correlations among their alternatives. Decoherence explains why those alternatives cease to interfere in any practical way. Yet the appearance of one definite world remains tied to the deeper problem of measurement. The cat became famous because it places the mystery somewhere familiar. A single particle in superposition may seem abstract. A living creature connected to that particle makes the consequences impossible to dismiss. The real paradox is not that a cat might somehow be half alive and half dead. It is that the same quantum rules that describe microscopic experiments so accurately appear to extend all the way into the ordinary world, where possibility has somehow become fact. Quantum superpositions are delicate. Their different components must preserve a stable phase relationship if they are to interfere. In a perfectly isolated system, that coherence can continue for a long time. In the ordinary world, however, isolation is extremely difficult. Every object is surrounded by an environment. Air molecules collide with it. Thermal radiation is emitted and absorbed. Stray electric and magnetic fields pass through the surrounding space. Surfaces vibrate. Internal particles move and interact. Each of these processes can become connected with the state of the quantum system. The result is decoherence. Decoherence is the process through which a quantum system becomes entangled with uncontrolled degrees of freedom in its environment. The system does not simply receive a large physical knock. Instead, information about the different components of its superposition spreads into the surrounding world. Heinz-Dieter Zeh was one of the earliest physicists to recognize the importance of this process. Beginning in the late 1960s, he argued that environmental interactions could explain why quantum interference becomes unobservable in macroscopic systems. Wojciech Zurek later developed the modern theory of decoherence in much greater detail. His work helped show how stable classical properties can emerge from quantum interactions without requiring a sharp boundary between the microscopic and macroscopic worlds. Consider a particle in a superposition of two positions. If the particle remains perfectly isolated, the two position components may retain a stable relative phase. They can later be recombined, allowing interference to appear. Now imagine that a photon scatters from the particle. If the photon leaves in one direction, when the particle occupies the first position, and a slightly different direction when it occupies the second, the photon carries information about which alternative occurred. The particle and photon become entangled. One component of the combined state links the first particle position with one photon state. Another links the second position with a distinguishable photon state. The phase relationship has not necessarily been destroyed from the perspective of the complete combined system. It has become shared between the particle and the photon. If the photon escapes into the environment and is never controlled again, recovering that phase information becomes extraordinarily difficult. Now, replace the single photon with countless air molecules, thermal photons, vibrations, and internal motions. Each interaction carries away another small record of the alternatives. The environment begins to function like an enormous measuring apparatus. It continually acquires information that distinguishes one part of the superposition from another. The quantum phase relationships become dispersed across an immense number of environmental degrees of freedom. A degree of freedom is simply an independent way in which a physical system can vary. The position of one molecule is a degree of freedom. Its momentum is another. Its rotation, vibration, and internal energy can add many more. A room contains an almost unimaginable number of such variables. Once information about a superposition has spread across them, direct interference between the original alternatives becomes practically inaccessible. Reversing the process would require controlling the relevant states of vast numbers of particles with extraordinary precision. In principle, the full quantum state may still preserve its correlations. In practice, the phase information has vanished into the environment rather like one quiet conversation becoming lost inside an entire stadium. Decoherence should therefore be distinguished from ordinary disturbance. A rough collision may alter a particle's momentum and disrupt an experiment, but a strong kick is not always necessary. Even a gentle interaction can destroy observable coherence if it reveals enough information to distinguish the alternatives. A single scattered photon may carry very little energy while still recording where an object was located. The issue is not merely how violently the system was disturbed, it is whether the interaction made the components distinguishable. This explains why large and warm objects usually decohere far more rapidly than isolated microscopic systems. A large object presents a greater surface to surrounding particles and radiation. It contains many internal components capable of becoming entangled with one another. A warm object emits more thermal radiation and undergoes more internal motion than a cold one. An atom held in a high vacuum and cooled close to absolute zero can be protected from many environmental interactions. A trapped ion may preserve coherence for seconds, minutes, or longer under carefully controlled conditions. Certain superconducting circuits can maintain engineered superpositions long enough for quantum operations to be performed. A dust grain floating in ordinary air is in a very different situation. It is struck by enormous numbers of gas molecules and photons. A spatial superposition involving visibly separated positions may decohere in a tiny fraction of a second, often vastly shorter than a billionth of a second under everyday conditions. The exact time depends on the object, the separation between the alternatives, the temperature, and the environment. The general pattern is clear. Macroscopic spatial coherence is lost far too quickly for human senses to detect. This does not mean that quantum mechanics stops applying when an object becomes large. The fundamental equations do not contain a simple line stating that atoms are quantum while chairs are classical. Instead, classical behavior emerges gradually through interaction with the environment. Some states are more resistant to decoherence than others. Wojciech Zurek called these stable states pointer states. They are selected by the particular way a system interacts with its surroundings. For many macroscopic objects, approximate position states are especially stable. The environment constantly monitors location through scattered light, collisions, and other interactions. A chair in one place and the same chair in a noticeably different place leave distinguishable records throughout the room. Superpositions of widely separated positions therefore decohere extremely rapidly. Approximate position becomes robust. It can be measured repeatedly by different observers, and each observer can obtain compatible information without strongly changing the state. This helps explain why the classical world appears to contain objects with persistent locations. The environment does not preserve every imaginable quantum combination equally. It continually selects certain stable patterns and suppresses observable interference between alternatives that differ too strongly. For local measurements, decoherence makes a coherent superposition behave like an effective statistical mixture. The interference terms become inaccessible. Instead of observing amplitudes that reinforce and cancel, an observer sees alternatives that appear to possess ordinary probabilities. This is a major part of the transition from quantum behavior to classical experience. However, decoherence does not settle every aspect of the measurement problem. It explains why interference between macroscopic alternatives disappears and why certain classical states become stable. It does not by itself prove that only one component of the complete quantum state remains physically real. Different interpretations continue to disagree about that question. A collapse interpretation may treat one outcome as genuinely selected. The many worlds interpretation may regard the decohered alternatives as separate branches of a continuing universal state. Other approaches interpret the quantum state in relational, informational or statistical ways. Decoherence is compatible with several of these views. Its achievement is more specific and experimentally grounded. It explains how uncontrolled entanglement converts observable quantum coherence into effectively classical alternatives. The classical world therefore does not emerge because nature suddenly abandons quantum mechanics at a particular size. It emerges approximately through countless interactions spreading phase information into the environment. Visible superpositions are absent from everyday life not because large objects possess no quantum state, but because their alternatives become entangled with their surroundings almost immediately. The possibilities have not simply been waved away. Their coherence has been scattered into the world around them, leaving behind the stable, definite-looking reality that human senses are able to observe. Quantum mechanics does not contain a simple rule declaring that superposition belongs only to small things. The Schrödinger equation does not inspect an object, notice that it has become too large, and quietly replace quantum behavior with classical certainty. In principle, a molecule, a machine, or an entire planet can be assigned a quantum state. In practice, however, creating and observing a large superposition becomes increasingly difficult. Every added particle introduces more internal motion, more possible interactions, and more opportunities for the surrounding environment to acquire information about the alternatives. The obstacle is therefore not necessarily a fundamental size limit. It is the growing challenge of isolation, preparation, control, and measurement. Experiments have steadily pushed superposition toward larger systems. Electrons were among the first material particles shown to produce diffraction. Neutrons later displayed interference, despite being almost 2,000 times more massive than electrons. Individual atoms were then sent through interferometers, where their center of mass motion followed coherent alternative paths. The same principles were eventually extended to molecules. This progression is important because a molecule is not an elementary particle. It contains several atoms held together by chemical bonds. Those atoms vibrate, rotate, and interact internally. A sufficiently complicated molecule may contain hundreds or thousands of moving components, yet its overall motion can still behave quantum mechanically. In 1999, a research team associated with Anton Zeilinger and Markus Arndt at the University of Vienna demonstrated matter wave interference using fullerene molecules. A fullerene made from 60 carbon atoms resembles a tiny hollow cage. Its arrangement is often compared with the pattern of a football, although at less than 1/1000th of a meter across, it would make a rather impractical addition to a sports cupboard. The molecule is vastly larger and more massive than an electron. Nevertheless, when a beam of these molecules passed through a diffraction grating under carefully controlled conditions, the detected distribution displayed an interference pattern. Later experiments extended molecular interference to considerably larger and more complex compounds, containing hundreds and eventually thousands of atoms. Some of these molecules had masses measured in tens of thousands of atomic mass units. The precise meaning of these experiments requires care. The entire molecule is not duplicated into two independently observable copies. Instead, its center of mass state becomes coherently associated with alternative paths through the apparatus. The centre of mass is the weighted average position of all the matter within the molecule. Even though the atoms inside may vibrate and rotate, the molecule's overall motion can still possess a de Broglie wavelength and form a path superposition. The different routes later recombine, and their probability amplitudes interfere. Each molecule is eventually detected at one localized position, but many repeated detections reveal a wave-like distribution. The molecule may remain internally complex during its journey. It does not have to become perfectly motionless or lose every trace of thermal energy. What matters is that its internal activity and its surroundings do not acquire enough information to distinguish the paths. This becomes increasingly difficult as the molecule grows. A larger object interacts more readily with stray gas molecules and thermal radiation. If it emits a photon whose direction reveals which path it followed, coherence can be lost. If an air molecule collides with it differently along the two routes, that collision may also store path information. Molecular interference experiments therefore require extremely high vacuum. Removing most of the gas greatly reduces collisions. Temperatures must be controlled to limit thermal radiation and unwanted internal excitation. The apparatus must be shielded from stray electromagnetic fields, while vibrations from buildings, pumps, traffic, and even distant machinery must be suppressed. The gratings and detectors must also be constructed with extraordinary precision. A tiny movement that would be irrelevant in ordinary engineering can shift the phase of a matter wave enough to wash out the interference pattern. Another form of large-scale quantum behavior appears in superconducting circuits. When certain materials are cooled below a critical temperature, electrical current can flow without ordinary resistance. The current is carried collectively by paired electrons known as Cooper pairs. A superconducting quantum interference device contains a superconducting loop interrupted by one or more weak links called Josephson junctions. Under suitable conditions, the circuit can be prepared in a superposition involving different persistent current states. In simplified terms, one component may correspond to current circulating around the loop in one direction, while another corresponds to current circulating in the opposite direction. These currents involve the coordinated behavior of enormous numbers of electrons. Superposition therefore concerns a collective electrical property large enough to generate distinguishable magnetic effects. It would still be misleading to imagine every electron as an independent little traveller, simultaneously racing around the loop both ways. The superconducting circuit behaves as one coherent quantum system, and the alternative current states are components of its collective wave function. Experiments have demonstrated interference and coherent transitions between such states. Superconducting circuits can now be controlled as quantum bits, allowing their amplitudes and phases to be manipulated using microwave pulses. Mechanical systems provide another frontier. An optomechanical resonator is a small physical object whose motion interacts with light. It may take the form of a vibrating membrane, beam, mirror, or microscopic drum. By using carefully controlled laser fields and cryogenic cooling, physicists can reduce the resonator's motion until it approaches its quantum ground state. The quantum ground state is not complete stillness. Even at the lowest allowed energy, quantum uncertainty leaves a small amount of motion called zero-point motion. Reaching this regime allows researchers to investigate superpositions and non-classical states, involving the motion of an object containing many atoms. Levitated nanoparticles offer a related approach. A tiny particle can be suspended using optical electric or magnetic forces so that it avoids direct contact with a supporting surface. Removing that contact reduces one important route through which vibrations and thermal energy enter the system. Researchers have cooled the centre of mass motion of levitated particles toward the quantum regime and produced controlled quantum delocalization, creating a widely separated spatial superposition, and later demonstrating clear interference remains a more demanding goal. These efforts are scientifically valuable because they test whether ordinary quantum mechanics continues to hold as mass, separation, and complexity increase. Some objective collapse theories predict that sufficiently large spatial superpositions should disappear, even in perfect isolation. According to those proposals, collapse would be a genuine physical process whose effects become stronger as more matter is involved. Molecular interferometers, superconducting circuits, optomechanical resonators, and levitated particles can therefore search for departures from standard quantum predictions. So far, experiments have continued to confirm quantum behavior across every scale at which coherent superpositions have been successfully controlled. This does not mean that physicists have placed a visible chair in two widely separated parts of a room. No naked eye object has been prepared in a spatial superposition resembling the popular image of Schrödinger's cat. Some systems are macroscopic in the number of particles participating or in the collective property being controlled. That is different from placing an entire everyday object into two clearly separated locations. The boundary between quantum and classical behavior therefore remains less like a wall and more like an increasingly difficult experimental landscape. Quantum theory supplies no obvious maximum size. The environment supplies countless opportunities for decoherence. As experimental control improves, researchers continue moving through that landscape, testing whether superposition truly extends without limit, or whether nature eventually introduces a boundary of its own. Superposition and entanglement are closely related, but they are not the same thing. A superposition describes a quantum state containing a coherent combination of possible alternatives. Entanglement describes a special relationship between two or more quantum systems, where the combined state cannot be separated into independent states for the individual parts. The distinction becomes clearer with a simple example. Imagine a single photon travelling through an interferometer with two available paths. Its quantum state may contain one amplitude associated with the first path and another associated with the second. As long as those paths remain coherent, the two amplitudes can later interfere. That photon is in a path superposition. There is only one system being described, and the alternatives concern two possible routes available to that system. No second particle is required. Now consider two particles whose spins have been prepared together. The combined state might contain one component in which the first particle is spin up and the second is spin down. It may also contain another component in which the first is spin down and the second is spin up. Neither component by itself gives the complete state. The system is described by a coherent superposition of two relationships. In the first alternative, the particles have one pattern of opposite results. In the second, those results are reversed. This is an entangled state. The important feature is not merely that each particle has more than one possible outcome. It is that the possible outcomes of the two particles are linked in a way that cannot be reduced to separate descriptions. The combined system has a well-defined quantum state, but neither particle necessarily possesses its own independent pure state. A pure state is the most complete quantum description that can be assigned to a system. When two particles are entangled, the pure state belongs to the pair as a whole. Looking at either particle alone gives an incomplete local description, often resembling a statistical mixture. This produces one of the most unfamiliar features of quantum mechanics. The whole can possess more definite structure than either of its parts. Entanglement therefore extends the idea of superposition. In an ordinary superposition, the alternatives may belong to one particle, such as two paths, two energy levels, or two spin states. In an entangled superposition, the alternatives describe relationships among several systems. One component may connect a result for the first particle with one result for the second. Another component contains a different pattern of correlations. Those relationships can remain meaningful even when the particles are widely separated. It is useful to compare this with an ordinary classical correlation. Imagine placing a red card in one envelope and a blue card in another. The envelopes are mixed and sent to distant locations. When one envelope is opened and found to contain the red card, the other is immediately known to contain the blue card. Nothing mysterious has travelled between them. The cards had definite colours all along. Opening one envelope merely reveals information about a pre-existing arrangement. Entangled particles cannot generally be explained so simply. One might try to imagine that each particle carries a hidden set of predetermined answers for every possible measurement. The apparent randomness would then arise only because the observer does not know those hidden values. In 1964, the physicist John Stuart Bell showed that this broad class of explanations has testable limitations. Bell considered theories in which measurement outcomes are determined by local hidden variables. Locality means that events at one location cannot be instantly influenced by a freely chosen measurement performed far away. Hidden variables are additional properties that supposedly determine the outcomes while remaining absent from standard quantum mechanics. Bell derived mathematical limits on the correlation such theories could produce. These limits became known as Bell inequalities. Quantum mechanics predicted that entangled particles could violate those inequalities. The difference was not philosophical decoration. It could be tested in a laboratory. Beginning in the 1970s and continuing through increasingly precise experiments, researchers measured entangled particles under different detector settings. Alan Aspect and his colleagues carried out especially influential tests in the early 1980s, using entangled photons and rapidly changing measurement arrangements. Later experiments improved the distances, detector efficiencies, timing, and control of possible experimental loopholes. Their results repeatedly agreed with quantum mechanics and violated Bell inequalities. These violations show that the observed correlations cannot generally be reproduced by local hidden variable models, satisfying Bell's assumptions. They do not prove that information can be transmitted faster than light. Each observer measuring one member of an entangled pair still sees an individually random result. The first observer cannot choose whether spin up or spin down appears. Without that control, no message can be encoded into the outcome. Only when the two observers later compare their records through ordinary communication do the correlations become visible. Entanglement is therefore non-local in the structure of its correlations, but it does not provide a device for sending an instant message across space. The universe remains inconveniently resistant to faster-than-light texting. The relationship between entanglement and superposition also helps explain decoherence. Suppose a particle is in a superposition of two paths. If an air molecule scatters differently from each path, the particle becomes entangled with that molecule. One component of the combined state links the first path with one environmental state. Another links the second path with a distinguishable environmental state. As more photons, molecules, vibrations, and internal motions become correlated with the alternatives, the original system becomes entangled with an enormous environment. The phase information required for simple interference is spread through those correlations. When the particle is examined by itself, its coherent superposition begins to behave like an effective mixture. Entanglement is therefore not only a source of remarkable long-distance correlations, it is also one of the main mechanisms through which observable quantum coherence disappears into the environment. The same phenomenon has become a practical resource. Quantum teleportation uses shared entanglement, a local joint measurement, and ordinary classical communication to transfer an unknown quantum state from one system to another. The original physical particle does not travel through space, and the process does not occur faster than light. Quantum cryptography can use entangled correlations to reveal interference or attempted interception. Quantum computers use carefully controlled entanglement among quantum bits to represent and manipulate relationships that become extremely difficult to reproduce classically. Entanglement also supports precision measurements, quantum networks, and increasingly demanding tests of the foundations of physics. Yet it remains important not to use the terms interchangeably. A single photon in a coherent combination of two paths is in a superposition, but it is not necessarily entangled with another independent system. two particles in a non-separable combined state are entangled. Their state includes superposition in an appropriate description, but its defining feature is the inseparable relationship between the parts. Every entangled pure state involves a superposition of correlated alternatives in some basis. Not every superposition involves entanglement. Superposition allows one quantum system to contain several coherent possibilities. Entanglement binds the possibilities of multiple systems into one shared state. The difference is subtle, but it is fundamental. Superposition concerns the alternatives within a quantum description. Entanglement concerns how those alternatives connect separate parts so deeply that only the whole possesses the complete story. Quantum superposition produces measurable effects, but physicists do not agree on what its mathematical components represent physically. The experimental predictions are not the main source of disagreement. Interference patterns, atomic spectra, quantum tunneling, and controlled superpositions have been observed repeatedly. The calculations work with extraordinary accuracy. The deeper question is, what exists before a definite measurement result appears? Does the wave function describe a real physical object? Does each component represent an equally real possibility? Is the wave function only a tool for predicting observations? Or does one actual particle follow a definite path, while an accompanying quantum wave explores several alternatives? These questions belong to the interpretation of quantum mechanics. The Copenhagen interpretation is associated particularly with Niels Bohr and Werner Heisenberg, although there was never one perfectly uniform Copenhagen doctrine. Its central emphasis is operational. Quantum mechanics provides rules for predicting the results of experiments. The wave function represents the possible outcomes and their probability amplitudes, while a measurement produces one definite recorded result. Niels Bohr stressed complementarity. The properties revealed by a quantum system depend on the experimental arrangement used to examine it. An apparatus designed to reveal interference does not simultaneously provide complete path information. A setup designed to identify the path removes the conditions required for full interference. Within this broad approach, asking what the particle was really doing between preparation and measurement may be treated as either physically incomplete or experimentally meaningless unless a measurement procedure is specified. The wave function evolves according to the Schrödinger equation until measurement, when the description is updated to match the observed result. This approach is practical and closely connected to laboratory work. It tells physicists how to calculate outcomes without requiring a detailed picture of an unseen microscopic reality. Yet it leaves an obvious question. Why should measurement be treated differently from every other physical interaction? Hugh Everett III proposed a radically different answer in 1957. His relative state formulation, later associated with the many worlds interpretation, removes fundamental collapse. The universal wave function always evolves according to the Schrödinger equation. When a measurement occurs, the system becomes entangled with the apparatus and observer. One component of the combined state contains one result and an observer who recorded it. Another component contains a different result and a correspondingly different record. Environmental decoherence prevents those components from interfering in ordinary conditions. They behave as effectively separate branches. From within one branch, an observer experiences only one outcome. The other components have not been physically destroyed. They remain within the larger wave function, but are no longer accessible through ordinary interaction. Everettian interpretations therefore take superposition very seriously. The components of the wave function are not merely unrealized possibilities, they belong to the continuing quantum state. The description is often summarized by saying that the universe splits, although branching through decoherence is subtler than a sequence of cleanly timed duplications. A different route was developed through pilot wave theory. Louis de Broglie first proposed a guiding wave picture during the early development of quantum mechanics. David Bohm later produced a complete non-relativistic formulation in 1952. In Bohmian mechanics, particles possess definite positions at all times. An electron in a double-slit experiment follows one actual trajectory through one region of space. The wave function, however, passes through both available paths and guides the particle's motion. It can contain several branches, including branches through routes not occupied by the particle. Those unused branches are not necessarily irrelevant. When they overlap again, their interference affects the guiding structure, and therefore influences the trajectory of the particle. Pilot wave theory restores definite configurations, but it does not restore ordinary classical physics. Its guiding dynamics are explicitly non-local when entangled systems are involved. Here, superposition belongs to the guiding wave function, while the material configuration remains definite. Objective collapse theories offer another possibility. Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber proposed a model in which wave functions undergo rare, spontaneous localization events. These events would be extremely uncommon for individual microscopic particles, but increasingly important for systems containing enormous numbers of particles. A microscopic superposition could therefore survive, while a macroscopic superposition would rapidly collapse into one definite alternative. Related continuous spontaneous localization models replace occasional sudden events with an ongoing random process. Roger Penrose has proposed that gravity may make superpositions involving significantly different distributions of mass unstable. In this view, a state associated with two sufficiently different space-time geometries may collapse after a characteristic time. These proposals modify standard quantum dynamics. That makes them more than interpretations in the narrowest sense, because they can potentially produce experimentally different predictions. No objective collapse mechanism has yet been confirmed. Experiments with increasingly massive systems continue to test whether superposition fails beyond some scale. Carlo Rovelli's relational quantum mechanics approaches the issue differently. It proposes that physical properties are not always absolute features possessed independently by a system. A property becomes definite relative to another system through interaction. An electron may have a definite result relative to a detector that has interacted with it, while another system that has not yet interacted with the detector may describe the larger arrangement differently. There is no need for one universally privileged observer. Any physical system can establish relational facts through interaction. Superposition, in this account, reflects how one system describes another when no definite relational value has yet been established between them. Quantum Bayesian approaches move further toward treating the wave function as a representation of expectations. Christopher Fuchs, Rudiger Schack, and Carlton Caves helped develop this family of ideas. The quantum state is understood not as a directly physical wave existing independently in the world, but as an agent's organized expectations about the consequences of possible actions and measurements. The Born rule provides a consistent way to relate those expectations. Measurement updates the agent's beliefs after a new experience. This does not mean that reality itself is imaginary. It means that the wave function may belong to the description used by an observer, rather than to the physical system in the same direct way as mass or electric charge. These interpretations disagree sharply about what exists. The Copenhagen tradition emphasizes measurement and operational predictions. Everettian accounts preserve every component of the universal wave function. Pilot wave theory combines definite particle configurations with a guiding wave. Objective collapse theories physically eliminate large superpositions. Relational quantum mechanics makes properties relative to interactions. Quantum Bayesian approaches interpret the state through structured expectations. Most of these approaches reproduce the same predictions for ordinary experiments. That agreement makes them difficult to distinguish experimentally. The interpretations often differ most strongly in situations where all accessible measurements give the same statistics. Objective collapse models are an important exception because they can predict small departures from standard quantum mechanics. Experiments continue searching for such effects. What is firmly established is that coherent quantum states produce interference. Their amplitudes can be prepared, manipulated, separated, recombined, and measured. What remains unsettled is what those amplitudes mean when no measurement has selected a definite record. Superposition unquestionably exists as part of the successful mathematical structure of quantum theory, and as a source of observable experimental consequences. Whether every component represents a physical reality, an unrealized possibility, a guiding influence, a relative description, or an expectation depends on which interpretation is adopted. The effects are secure, the picture behind them is not. Quantum mechanics tells us with extraordinary precision how possibilities behave. After more than a century, physicists are still deciding what kind of existence those possibilities possess. A quantum computer begins with a deceptively simple idea. Instead of storing information only in ordinary bits, it uses quantum bits. A classical bit has one of two definite values. It may represent 0 or 1, off or on, false or true. A quantum bit also has two computational basis states, but it can occupy a coherent superposition of them. This means that its state may contain one probability amplitude associated with 0 and another associated with 1. The amplitudes determine the probabilities of the two possible measurement results, while their relative phase influences how the quantum bit behaves during later operations. A quantum bit is not one particular kind of object. It is any sufficiently controllable quantum system with two usable states. Trapped ions can act as quantum bits through carefully selected internal energy levels. An electron spin may use spin up and spin down. A photon can encode information in two polarizations or paths. Neutral atoms can be held in arrays using laser light. Superconducting circuits can behave as artificial atoms with two controlled quantum states. Each platform has different strengths and difficulties, but all depend on the same basic requirement. The two states must remain coherent long enough to be prepared, manipulated, entangled, and measured. Quantum computing is often described by saying that a machine tries every possible answer at once. This is memorable, but it is also misleading. A quantum computer cannot simply calculate an enormous list of answers and then display every result. When a collection of quantum bits is measured, only one ordinary classical result appears. A register of quantum bits produces one bit string in each run. It might return a sequence corresponding to 0, 1, 1, 0, or some other definite arrangement. The detector does not reveal the complete collection of amplitudes that existed before measurement. This limitation is central. The value of superposition is not that every possible answer becomes directly readable. It is that the amplitudes associated with different computational possibilities can be deliberately transformed and allowed to interfere. A useful quantum algorithm is designed so that amplitudes connected with unwanted outcomes tend to cancel through destructive interference, while amplitudes connected with useful outcomes reinforce through constructive interference. The calculation therefore shapes the final probability distribution. When the quantum register is measured, the desired result appears with a higher probability than it would have without the carefully arranged interference. The algorithm may need to be repeated several times, but the useful answer has been made more likely. The theoretical foundations of quantum computation were developed through work by several physicists and mathematicians. David Deutsch played a particularly important role during the 1980s by describing a universal quantum computer capable of simulating any finite physical process permitted by quantum mechanics. His work helped establish that quantum computers were not merely specialized laboratory curiosities. In principle, they could perform general computations using quantum gates, just as ordinary computers perform general computations using classical logic operations. A quantum gate changes the amplitudes or phases of one or more quantum bits. Some gates rotate an individual quantum state. Others create entanglement between different quantum bits, A sequence of gates forms a quantum circuit. The order and design of those gates determine how the computational alternatives interfere. The growth of the quantum state space is one reason these systems are powerful and difficult to simulate. One quantum bit has 2 computational basis states. 2 quantum bits have 4. 3 have 8. Each additional quantum bit doubles the number of basis states in the combined description. 10 quantum bits have 1024 basis states. 20 have more than 1 million. 50 have more than 1 quadrillion. A sufficiently large register therefore requires an enormous number of amplitudes to describe fully using a conventional classical computer. This does not mean that a quantum processor gives direct access to every one of those numbers. Measurement still produces only 1-bit string. The challenge is to manipulate the full state so that the limited information extracted at the end answers a carefully chosen question. Peter Shor demonstrated one of the most famous examples in 1994. Shor's algorithm can factor large integers using a quantum computer more efficiently than the best widely known classical methods. Factoring means finding the smaller integers whose multiplication produces a given number. The algorithm does not simply test every possible factor and read out the correct one. It converts the factoring problem into a problem involving periodicity. A quantum procedure creates a superposition of possibilities and then uses interference through a quantum Fourier transform to reveal information about that hidden period. The final measurement provides only part of the answer, but classical processing can use that information to recover the factors with high probability. The significance of Shor's algorithm is partly practical. Many current cryptographic systems rely on the difficulty of factoring sufficiently large numbers using classical computers. A large, reliable quantum computer could threaten those systems. Love Grover introduced another important algorithm in 1996. Grover's search algorithm examines an unstructured collection of possibilities using roughly the square root of the number of steps required by a straightforward classical search. If there are 1 million possible entries, a classical search may require close to 1 million checks in the worst case. Grover's method requires roughly 1,000 quantum iterations under ideal conditions. The algorithm works through amplitude amplification. The amplitude of the desired result is repeatedly increased, while the amplitudes of the alternatives are adjusted through interference. The advantage is substantial, though less dramatic than the exponential improvement associated with some other quantum algorithms. Both examples reveal the same principle. Superposition alone is not enough. A randomly prepared collection of quantum amplitudes is not automatically useful. The phases must be controlled with great precision. Entanglement must be created where the algorithm requires correlations. Quantum gates must guide the amplitudes through an organized sequence of transformations. Then the alternatives must be recombined so that interference concentrates probability in the useful parts of the state. This delicacy also creates the central engineering problem. Quantum systems interact with their surroundings. Heat, stray electromagnetic fields, imperfect laser pulses, vibrations, material defects, and uncontrolled coupling can alter the amplitudes and phases. These effects cause errors and decoherence. Once the relative phase between components is lost, the alternatives can no longer interfere in the intended way. A quantum computation may then produce little more than an expensive collection of random answers. Researchers at International Business Machines, Google Quantum Artificial Intelligence, Quantinuum, IonQ, and many university laboratories are developing different process designs while trying to improve coherence times, gate accuracy, measurement reliability, and scalability. No physical platform has removed the problem entirely. Quantum error correction offers a possible route forward. It protects logical quantum information by distributing it across many physical quantum bits. This is more subtle than making an ordinary backup copy. The no-cloning theorem states that an unknown quantum state cannot be copied perfectly through a universal physical process. Quantum error correction therefore does not measure the complete state or duplicate it directly. Instead, It stores the information in carefully designed entangled patterns. Additional measurements reveal whether certain kinds of errors have occurred without exposing the encoded quantum information itself. Corrective operations can then restore the logical state. The cost is considerable. One reliable logical quantum bit may require many physical quantum bits, especially when operations and measurements remain imperfect. Quantum computing therefore turns superposition into a demanding technological resource. The quantum bit can contain coherent alternatives, but those alternatives become useful only when their amplitudes and phases remain under control. They must be transformed with purpose, protected from the environment, and brought back together through interference. A quantum computer does not gain power merely because one thing can represent two possibilities. It gains power because those possibilities can interact mathematically before one definite answer is finally measured. Quantum superposition is not only something physicists observe in carefully isolated experiments, it can also be used as a measuring tool. When a quantum system occupies a coherent superposition, the different components of its state can evolve along slightly different paths. Time, gravity, acceleration, rotation, magnetic fields, and electric fields may affect those components by different amounts. The result is a change in their relative phase. That phase difference may be extremely small, but when the components are recombined, it alters the interference pattern. A weak influence that would otherwise be difficult to detect can therefore become visible as a shift in the final measurement probabilities. Atom interferometers use this principle with matter waves. A cloud of atoms is first cooled until its random motion becomes very small. Laser cooling techniques developed through the work of Stephen Chu, Claude Cohen-Tanuji, William Daniel Phillips, and many other researchers made this level of control possible. The cooling does not bring the atoms to complete stillness. Quantum uncertainty prevents that. Instead, it reduces their thermal motion enough for their wave-like behavior to be manipulated precisely. Carefully timed laser pulses can then act as beam splitters for atomic matter waves. The laser does not physically cut an atom into two smaller pieces. It transfers momentum in a controlled way, preparing the atom's center of mass state as a superposition of two different trajectories. Later pulses redirect those trajectories like mirrors and eventually bring them back together. If the two paths have experienced slightly different conditions, their phases no longer match exactly. When they recombine, the difference affects which final atomic state is measured. Earth's gravitational field provides one important example. Atoms traveling along slightly different vertical paths experience different gravitational potentials and different accelerations. The resulting phase shift can be used to measure gravitational acceleration with remarkable precision. Related instruments may contribute to navigation systems that do not rely continuously on satellite signals. They may also help detect underground structures, variations in rock density, buried cavities, or changes in groundwater by sensing tiny differences in the local gravitational field. In geophysics, such measurements could improve surveys of volcanoes, faults, and subsurface movement. Atom interferometers can also test the equivalence principle, the idea that different forms of matter fall in the same way when other influences are removed. Superposition is equally useful when the alternatives involve internal atomic states rather than separate paths. Ramsey interferometry prepares an atom in a coherent combination of two energy states. Those components accumulate relative phase as time passes. A later electromagnetic pulse recombines them, allowing the phase difference to be measured. This principle supports atomic clocks and extremely precise frequency standards. A tiny mismatch between an applied frequency and the atom's natural transition frequency gradually produces a measurable phase shift. Quantum magnetometers work in a similar way. Atomic spins can be prepared in superpositions that respond sensitively to magnetic fields. Even a very weak field can alter the rate at which the spin phase evolves. By measuring the final state, researchers can infer the strength and direction of the field. Nitrogen vacancy centers in diamond provide another useful platform. A nitrogen vacancy center is a small defect in the crystal structure of diamond, involving a nitrogen atom beside a missing carbon atom. Its electronic spin can be prepared, manipulated and read using light and microwaves. Because the spin responds to local magnetic and electric conditions, nitrogen vacancy centers can act as microscopic sensors. They can probe magnetic fields produced by materials, electrical currents, and potentially individual molecules at extremely small distances. Quantum techniques also improve some measurements that are not based primarily on matter wave superposition. Gravitational wave observatories such as the Laser Interferometer, Gravitational Wave Observatory use large-scale laser interference to measure tiny changes in distance. Their main interference pattern is produced by electromagnetic fields that can often be described classically. However, the sensitivity of the instruments is partly limited by quantum fluctuations in the light. Specially engineered squeeze states can reduce uncertainty in the particular optical quantity most important for the measurement. The uncertainty is not removed entirely. It is redistributed, reduced in one variable while increasing in another. This allows selected measurements to become more precise than they would be using ordinary light. Every quantum sensor must solve the same delicate problem. The system must be protected from unwanted influences such as thermal motion, stray fields, vibrations, collisions, and environmental noise. At the same time, it must remain sensitive to the one influence being measured. Too much isolation, and the sensor learns nothing. Too much interaction, and coherence disappears. The art lies in allowing gravity, time, acceleration, rotation, or a field to alter the relative phase while preventing everything else from doing the same. Superposition turns weak effects into detectable interference. The alternatives separate, gather slightly different phases, and then meet again. Most practical quantum sensors therefore look less like science fiction objects existing visibly in two places and more like exquisitely controlled interference experiments. The system remains one quantum object. Its alternatives experience the world differently for a brief time, and their reunion reveals what happened along the way. Quantum superposition is often summarized by saying that a particle can be in two places at once. The phrase is memorable, but it can also create the wrong picture. It may suggest a tiny solid object appearing as several identical copies, each sitting in a different ordinary location. One miniature electron is imagined on the left, another identical electron on the right, and both are somehow treated as the same particle. That is not usually the most accurate way to understand position superposition. A position superposition is a property of the quantum state. The state contains probability amplitudes associated with different possible detection locations. Those amplitudes can evolve, acquire relative phases, and interfere before a measurement produces one recorded result. The detector does not normally find several complete electrons scattered across the apparatus during a single run. It records one localized event carrying the full electric charge of the electron. The alternatives belong to the state that determines the probabilities, not necessarily to a set of independently existing classical spheres. Another common myth is that superposition lasts until a conscious person looks at the system. In laboratory physics, human awareness is not required. A photon can scatter from a particle, an air molecule can collide with it, or a detector can become correlated with its path. These interactions may store information that distinguishes the components of the superposition. Once the alternatives become entangled with sufficiently different environmental states, observable coherence can disappear. This may happen long before anyone checks the apparatus. A computer can record a result in an empty room. The file may remain unopened. The physical interaction has still occurred. The universe does not require a witness leaning over the detector with an especially thoughtful expression. Superposition also does not mean that every imaginable possibility exists with equal importance. A quantum system does not include any outcome that can be casually invented. Its possible states are constrained by its physical preparation, energy, geometry, conservation laws, interactions, and the structure of the apparatus. An electron approaching two open slits may possess amplitudes associated with both routes. It does not therefore possess an equal amplitude for appearing inside a distant teapot or wandering off toward another galaxy. Even among the physically available outcomes, the amplitudes may differ greatly. One possibility may be highly likely, another unlikely, and a third may have zero probability, because interference has cancelled its amplitude completely. Superposition means that several allowed components contribute coherently. It does not mean that nature distributes equal attention to everything conceivable. A further misconception treats superposition as ordinary ignorance. Imagine that a coin has landed beneath a hand. It is already heads or tails, although the result is hidden. A list assigning equal probabilities to both outcomes describes the observer's uncertainty. A coherent quantum superposition contains more than this. Its components possess relative phases. When they are recombined, their amplitudes can reinforce or cancel. This produces interference patterns that cannot generally be reproduced by assuming that the system secretly possessed one definite classical state all along, and the observer merely failed to discover it. A classical mixture adds probabilities. A coherent superposition adds amplitudes before probabilities are calculated. That difference is experimentally measurable. The expression both at once can still be useful, especially as a first introduction. It captures the fact that more than one alternative belongs to the quantum description. But it becomes misleading when it suggests that one experiment reveals two separate classical outcomes simultaneously. An electron in a two-path superposition is not normally observed following both routes as two visible objects. One final detection appears. The evidence for both path amplitudes lies in the interference pattern formed over many repetitions. The phrase should therefore point toward the structure of the state, not toward a literal photograph of several copies. Quantum behavior is also not restricted by a simple rule saying that it occurs only at extremely small distances. The visibility of superposition depends on several factors. Isolation matters, temperature matters, mass, internal complexity, environmental coupling, preparation, and measurement precision all matter. A large separation between two-path components may make them easier for the environment to distinguish, causing faster decoherence. Yet atoms and molecules can remain coherent across distances much larger than their own physical size, when experimental conditions are carefully controlled. Conversely, even a microscopic particle can lose coherence quickly in a noisy environment. Size is important, but it is not the only deciding factor. Superposition does not provide a method for traveling instantly between locations. It does not allow information to be sent into the past. It does not let an observer examine every possible branch and choose a favorite result afterward. A quantum state may contain many amplitudes, but measurement returns limited information. Entanglement can produce correlations across large distances, yet those correlations cannot be used to transmit a controllable message faster than light. Quantum eraser experiments do not rewrite earlier events. They reveal different correlations when measurement results are sorted in different ways. The theory is strange enough without quietly lending it a time machine. Metaphors can help, but each one has limits. A hidden coin illustrates classical uncertainty, but it does not interfere with itself. Water waves demonstrate addition and cancellation, but a quantum wave function is not simply a material fluid spreading through space. Branching roads suggest alternative paths, yet ordinary travellers choose one route and do not produce interference when the roads meet again. Overlapping musical notes capture the idea of combination and phase, but they remain directly measurable disturbances of air rather than probability amplitudes. No single image contains the whole meaning. Each analogy illuminates one feature while leaving another in shadow. A more precise statement is this: a quantum state can contain coherent probability amplitudes associated with several distinguishable outcomes. Those amplitudes may evolve together and interfere before a measurement produces one definite recorded result. This avoids imagining several ordinary copies while preserving what makes superposition physically important. The system is described by one complete quantum state. Its components are possibilities connected through amplitudes and relative phase. Their interference influences what can be observed. Superposition is therefore neither simple duplication nor ordinary uncertainty. It is a structured relationship among possible outcomes, hidden from direct view, but revealed through the patterns those possibilities create when they are allowed to meet again. Quantum mechanics has survived every well-controlled experimental test of superposition so far. Electrons, photons, atoms, molecules, superconducting circuits, and mechanical systems have all displayed behavior consistent with coherent quantum states. As experiments have become more precise, the theory has continued to predict the results with remarkable accuracy. No confirmed boundary has been found where an isolated system simply becomes too large for superposition. Yet the measurement problem leaves open an intriguing possibility. Perhaps the apparent collapse of a wave function is not only an effective consequence of environmental decoherence or a rule used to update predictions. It may represent a genuine physical process that has not yet been directly identified. Objective collapse theories explore this idea. One influential proposal was developed by Giancarlo Ghirardi, Alberto Rimini, and Tullio Weber. In the Ghirardi-Rimini-Weber theory, particles undergo spontaneous localization events. For an individual microscopic particle, such an event would be extraordinarily rare. Its wave function could remain spread across several possibilities for a very long time. For a large object containing an enormous number of particles, however, the chances accumulate. If any one constituent undergoes localization while strongly connected to the others, the state of the whole object can become localized extremely quickly. Microscopic superpositions would therefore survive, while macroscopic objects would appear definite. Continuous spontaneous localization offers a related approach. Instead of occasional sudden jumps, the wave function is subjected to a continuous random localization process. The effect would remain extremely weak for small systems, but grow increasingly significant as more matter becomes involved. These models modify standard quantum mechanics. They do not merely reinterpret the existing equations. As a result, they can predict small experimental differences, including possible loss of interference, tiny heating effects, or spontaneous radiation. Gravity has also been proposed as part of the answer. Roger Penrose has argued that a superposition involving two significantly different distributions of mass may also involve two different space-time geometries. Since general relativity treats gravity as the geometry of space-time, combining those geometries may be fundamentally unstable. According to this proposal, the greater the gravitational difference between the alternatives, the more quickly the superposition should collapse. This remains speculative. Gravitationally induced collapse is not an established prediction of general relativity, and it is not part of standard quantum mechanics. Experiments are searching for these possible failures in several ways. Molecule interferometers test whether increasingly massive objects continue to produce interference. Levitated particles may eventually allow larger spatial superpositions to be prepared with reduced contact with the environment. Mechanical resonators can be cooled toward their quantum ground states and examined for unexplained loss of coherence. Other experiments search for spontaneous radiation or excess heating that collapse models might produce. Precision measurements place limits on how frequently localization events could occur and how strongly they could affect matter. Research at universities, national laboratories, and institutions including the European Organization for Nuclear Research contributes to broad tests of quantum theory. Particle colliders, however, do not directly solve the measurement problem. Their relevance lies in testing quantum predictions and searching for new physics, not in watching wave functions visibly collapse. Another line of investigation concerns macrorealism. Macrorealism is the idea that a macroscopic system possesses definite properties at all times, independently of whether those properties are measured. Anthony Leggett and Anupam Garg derived an inequality that allows certain forms of macrorealism to be tested experimentally. The Leggett and Garg inequality places limits on correlations measured at different times under specific assumptions. Quantum systems can violate those limits. Such violations suggest that the system cannot always be described as carrying one definite macroscopic value throughout the experiment, at least not while preserving all the assumptions used to derive the inequality. Interpreting these tests requires care. Experimental disturbance, imperfect measurements, and assumptions about how observations affect the system must all be considered. The same caution applies to every search for collapse. A disappearing interference pattern is not automatically evidence of new physics. Ordinary decoherence can produce the same appearance. Stray electromagnetic fields, thermal radiation, vibrations, gas collisions, internal molecular motion, material defects, and measurement errors can all destroy coherence. Researchers must calculate and suppress these effects before any remaining anomaly can be treated seriously. This makes the experiments exceptionally demanding. The larger the attempted superposition becomes, the harder it is to protect. The very systems most likely to reveal a new collapse mechanism are also the systems most vulnerable to ordinary environmental noise. Progressively larger superpositions nevertheless turn the problem into an empirical question. Instead of asking only where the quantum world ends, physicists can create controlled states, predict how long coherence should survive, and test whether nature follows the standard equations. So far it has. No confirmed breakdown of quantum superposition has been observed. No objective collapse mechanism has been detected, and no gravitational threshold has been established. But the accessible range of mass, complexity, separation, and coherence continues to expand. Quantum theory may remain valid without limit, or a new physical process may eventually emerge where experiments have not yet reached. For now, the boundary remains unseen, and every successful test quietly pushes it a little farther away. Quantum superposition allows one physical system to occupy a coherent state containing several possible properties or outcomes, even though measurement produces one definite record. The idea emerged as the classical categories of particle and wave began to fail. Thomas Young demonstrated that light produces interference. Max Planck introduced discrete energy quanta. Albert Einstein described light transferring energy through photons, and Louis de Broglie proposed that matter possesses wave-like properties. Quantum mechanics brought these discoveries together through the wave function and its probability amplitudes. Superposition follows from the linear structure of the theory. Different possible states can form one coherent quantum state, and their amplitudes may reinforce or cancel through interference. The double-slit experiment reveals this directly. Each electron or photon produces one localized impact, yet the accumulated pattern depends on amplitudes associated with both available paths. When an interaction records which path was taken, the alternatives become correlated with distinguishable states of a detector or the environment. Visible interference then disappears. The same principle appears in many forms. A photon can occupy a superposition of polarizations. An electron can combine different spin possibilities. An atom can occupy multiple energy states. A molecule can follow alternative paths, and a superconducting circuit can contain different persistent current states. Quantum bits turn these controlled alternatives into a resource for computation. A coherent superposition is not merely classical uncertainty. A hidden coin is already heads or tails, even when nobody knows which. Quantum amplitudes retain phase relationships and can interfere. A statistical mixture lacks that coherence, while entanglement describes inseparable correlations between several quantum systems. Decoherence explains why such behavior is rarely visible in ordinary life. Large objects continually interact with air, radiation, heat, vibrations, and their internal components. Information about their alternatives spreads into the environment, making interference effectively inaccessible. Quantum mechanics does not simply stop applying beyond a particular size. Classical behavior emerges gradually through these interactions. Physicists still disagree about what superposition ultimately represents. Its components may describe physical branches, guiding waves, relational properties, structured expectations, or states that eventually undergo objective collapse. These interpretations remain unsettled, but the experimental consequences are not. Atomic clocks, spectroscopy, quantum sensors, matter wave interferometers, and quantum computers already depend on controlled superposition. Microscopic reality is therefore not made from ordinary objects quietly carrying predetermined answers. It is described by quantum states whose possibilities combine, evolve, and interfere before one definite outcome enters the visible world.